small change in
If you
one,
want to talk, you can
uh,
sit somewhere
it
else.
would still be retained. It is not a, there's no targeted enrichment, so error is not enriched. So there were several very favorable points of using NGS in studying ancient DNA, and they studied a 38,000-year-old cave fossil, nuclear and mitochondrial DNA, and they found out that the divergence happened around 500,000 years ago. And paper actually predicted that with the technology that we now have in hand, within 2 years, we'll be able to provide the sequence of the nuclear DNA of the fossils of the Neanderthals. He did succeed, not in 2 years, but 4 years. In Science 2010, a draft sequence of the Neanderthal genome was provided. These came from three Neanderthal individuals. They compared it with five human individuals, and here they have used a
If you
targeted
are talking about
capture approach.
smart
And
people,
there was another, okay, sorry, there was another paper which provided the complete picture of mitochondrial DNA of Neanderthal. Now, another beautiful thing came. While he was studying Neanderthals, they found out that there was a new ancestor in the hominin lineage, and that is Denisovian. And we call it Denisovian because they were found out in a cave in Denisovia. What you see here is the cave. And within this cave, they this is the beauty of paleogenomics. The small piece that you see here is the bone that was used for sequencing. And just by using the bone, this bone here and some teeth, they could find out that there was a new ancestor which was never known before, Denisovian. Again, this was not an easy thing per se because the postdoc who was doing it had to sample 2,000 different bones to find out that we have a new ancestor. And this is how it goes. They sample the bones. They first analyze for the presence of collagen, a protein in it. If the collagen is intact, that means the sample is good enough to purify DNA. If collagen is not intact, it's trash. And again, if there is collagen, the next step is finding out whether the collagen comes from human or any other animals. If it is any other animals, again, it is not part of the study. And again, if the collagen is good and it is human, it will go for the next step. You purify the DNA, subject it to sequencing and find out the sequence. And this is what it is. Just a small bone and a teeth, and you know that we had a new ancestor. And not just that we had a new ancestor, they dipped into the family essays of this ancestor in the Denisonian cave. They sequenced other bones, and what they found out is that there was interbreeding between them. A Neanderthal woman and a Denisovian man had a daughter. So the daughter gene the sequence, and what they found is that the mitochondrial DNA, that is the mother from the mother's side, the mitochondrial DNA was entirely from the Neanderthal woman, while the nuclear DNA was shared between Neanderthal and Denisovian. So interbreeding was possible between Neanderthal and Denisovian. So yeah, this was when the Neanderthal nuclear DNA sequencing was completed in Nature 2014. And around 2019, COVID came. So what I wanted to stress here is that his study was not just about evolution. He tried connecting whatever was relevant at the time with evolution, and one thing is COVID. So during the time when he was studying COVID, he was studying about extinct Neanderthals and Denisovians, and this was the time when Homo sapiens were actually afraid that we would be extinct as well because of COVID. And during that time, what he found is that a subpopulation of human Homo sapiens who had a major genetic risk for developing COVID, like the COVID symptoms to be higher, this particular region was inherited from the Neanderthals. It was actually a 50 kilobase region, which was responsible for, increasing the risk for COVID. And this particular region was present in 50% people of South Asia and 16% people in Europe. And this region was actually inherited from Neanderthals. This region is not there in African population. Neanderthals, in fact, is not an African population. The modern humans originated in Africa, but Neanderthals had actually deviated out of, they had migrated out of Africa. People outside Africa have 1 to 2% of Neanderthal genes. That was with COVID. He also studied evolution of human brain. So this is from Science in 2022. What he found out is that a single amino acid change in trans-ketolase like one particular protein in the brain is enough to give increased neuronal synthesis in humans. As you can see here, in humans, the TKTL1, which is trans-ketolase like 1, has arginine, while in Neanderthals it is lysine. And this one amino acid change is enough to give a lot more neurons in humans than in Neanderthals. So I'll stop with that and say that Pebo, I mean, something which made him very different is that he was always at the edge. Whatever be the technological advancement at the time, whether it was starting from PCR all the way up 40 years later with the NGS, he still, I mean, he had one question, one strong question, but he was not afraid to change the technology. Starting from PCR, which was the first at the time, NGS, that was the first at the time, viral sequencing, which was the first at the time. He used all of these to answer the questions, and that is what he was doing. He was always at the edge and trying to push the edge, and that is what basically took him all the way to the Nobel. Thank you. I'll take question. Homo sapiens inheriting something from Neanderthals. Did we already establish that they're different species? The fact that in the tree also we see that there are two different species. Okay, so why is this question relevant? So the initial speciation was based on morphological evidence, right? So now what Pebo is bringing in is the genetic evidence. So something is, even when you say something is established, that is establishment in the limit of the technologies they have at the time, right? So it was established with morphological evidences, which may or may not be true when you bring in the genetic evidences, right? So what paper was trying to bring in was the genetic evidence into this. So it really resulted in reinforcing what was established before with morphology when it was. But if the morphological evidence and genetic evidences were contradictory, then we would have had to redraw the earlier established one, right? So now which one is they are both. They are both. They are complementing each other, thankfully. And then when we talked about the interbreeding between Neanderthals and Denisovans, so they interbred and they existed at the same time. They did exist at the same time, yes. So Homo sapiens also existed, but there is no evidence so far of interbreeding between Denisovan and Homo sapien or Neanderthal and Homo sapien so far. Yeah. Yeah. Yes. If there was no interbreeding between Neanderthal and Homo sapiens, then how did COVID give the similar type of genetic sequences found in humans? Okay, so this could be evolution, right? So some parts being conserved through the generation. Yeah, I believe. Yeah, good.
Can you give us a brief picture about where the Homo sapiens, Denisovans, and Neanderthals were, so that we know that the
I
gene pool was like?
Yeah, I mean I don't have a picture, but yeah, there are pictures where you have the map with where Denisovans, Neanderthals, and Homo sapiens are with the timelines, but I don't know.
Last week, there was a paper in paleoanthropology where they say that this, Neanderthals became extinct because of the sex with the humans, actually the Homo sapiens.
Yeah.
And it's only one way sex actually. The male of,
Male.
Neanderthals made with the
Female and
female
human.
humans.
Yeah.
That could be the reason of this only 2%.
Yeah. 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 I have read that paper. It is war it is sex and not war that killed the Neanderthals here. Yeah, it's a beautiful paper, but it was not from paper side, so I thought I'll not. Yeah. So there's a paper that it is not war, but sex that killed the Neanderthals. Yeah. Thank you so much.
Professor Anil Shaji has time and time again brought glory and fame to his institution, his elaborate and rigorous scientific research. After finishing his BSc from University College Tirunelveli, he obtained his MSc from IIT Madras. He did his PhD at the University of Texas and postdoc at the University of New Mexico. He joined as an assistant professor in the School of Physics in 2009. He is the present Dean of Academic Affairs. He is credited with numerous publications and is one of the recipients of various awards and recognitions for his excelling performance. Today, he is here with us to give his insight into this year's Nobel Prize for Physics.
Okay, so good morning, everyone. Uh, yeah, so let me thank the organizers of ANVESHA for giving me this chance to talk to you about the Nobel Prize in Physics 2022. I had talked about the Nobel Prize in Physics in 2012, which also went to the broad area of quantum technologies and quantum information theory. So 10 years later, again the same field is being recognized with the Nobel Prize in 2022, which went to three gentlemen. Alain Aspect, who is on the left with a big mustache and mistakable Alain Aspect. Last time around, it was Dave Wineland who was having handlebar mustache. This time, Alain Aspect has. So, some things to ponder for the guys out here, whether you want to emulate. Then John Clauser, he's a gentleman from a slightly previous generation, and Anton Zeilinger, about whom even the Nobel citation itself is not clear exactly why they gave him the Nobel Prize, but as was mentioned by Nishana in the previous talk, he is kind of a force of nature when it comes to pushing the boundaries of quantum tech. So it's really difficult to ignore Zeilinger's contribution, even though it happened a couple of decades after what Aspect and Clauser managed to do. Okay, so now to explain why their this honor is well deserved, it is a little bit of an arduous task for the uninitiated. So let's kind of take things slowly. So I'm going to develop or consider along with you a little bit of a game of chance. And the game of chance is controlled by the dealer who is in the middle. And what she has with her are two kinds of coins. There are gold colored coins and silver colored coins. And like all coins, they have two sides, heads or tails. Okay. So that's the starting point that the dealer has. And like all self-respecting casino dealers, she has thousands or even millions of such coins with her. So how does the game proceed? So what she does is that she picks according to whatever calculations that she has. She will pick either a gold or a silver coin and put it in a actually pick two coins at a time, put both of them in their own boxes and close the box. Okay. And the closed box is sent to two players who are maybe far apart. Let's imagine that they are quite far apart. Okay, they're far apart from each other. So they got player A and player B. And you got these guys, the messengers, who are carrying the closed boxes and taking it to the players A and B respectively. Now the players can ask the messenger one of two questions. That's all they can do. There are two possible questions that can each player can ask, and they can ask only one of them. So, what are the questions that the players can ask? One of the player A can ask whether the coin is gold or silver, or she can ask whether it's heads or tails. Okay. So, if the player asks gold or silver, the messenger's job is easy. Uh, the messenger just opens the box, shows the color of the coin, and walks back and goes back. So on the other hand, the player asks heads or tails. The messenger has to take the coin out of the box, toss it, and show the player which side comes up, and then picks up the coin and goes back. Now notice that the coin need not be unbiased or anything. The coin can be very well be biased. Okay. So what's the consequence of all this? So let's put in some notation which will be useful. If the player A asks the question gold or silver, that particular event we label it as A subscript GS. So A asked gold or silver. So it's as descriptive as it can be, right? So then if a player asks heads or tails, that will be denoted as AHT. You can similarly define BGS and BHT. That's just the same thing for player B. Okay. Now there is some reward for the game. Okay. So if player A asks gold or silver and the messenger opens the box and indeed the coin turns out to be gold, the first player, player A, gets plus 1 point. Or if you want high stakes gambling, you can say ₹1,000,000 or something like that. Doesn't matter. Okay. So let's keep it simple and say plus 1. If the player asking the question gets it wrong, if in the sense that sorry, not get it wrong, gets the other one, okay, it gets a wrong outcome in the sense that it's silver when he says that it's a gold, when he assumes that it's a gold coin, or let's keep it simple. When it's silver, he gets -1. Okay, so those are just point assignments. So if he asks gold or silver, he gets gold, he gets +1, gets silver -1. Similarly for heads or tails, he says heads or tails, he asks heads or tails, he gets heads, he gets +1, he gets tails -1. Just we are assuming points for each of the outcomes. Because there is no bias towards gold or silver, you can reverse the plus and -1, doesn't make a difference. Right. So the point is that these outcomes, therefore, four outcomes AGS, AHT, BGS, BHT are associated with two values plus or -1 depending on what happened. So what you have to remember here is that the probabilities of various events happening, whether it is AGS becoming +1, AGS becoming -1, or a BGS becoming +1 or -1, getting those rewards for each of those questions is completely controlled in this game by the dealer, because the dealer chooses the color of the coin that is sent, and the player she may have sent a silver coin, but player A asks gold or silver, and she gets -1 points because the coin is silver. She could have asked heads or tails instead, and maybe she may have won +1 points because after tossing it may have come as heads. But again, imagine that the dealer also chooses whether the coins are biased or not. She may be actually sending a coin so balanced that anytime you toss it, it is heads only. Okay, that coin also happen or tails only, whatever it is. Right. So now we are going to consider some products of these quantities. Okay. Products are HGS times BHT. Okay. So that product makes sense only when in one instance of the game, the player A asks the question GS and player B asks the question heads or tails. So if that's the scenario, then A may be associated with points +1 or -1 depending on whether it was gold or silver, and B may be associated with points +1 or -1, well, depending on whether heads or tails showed up. So you are literally taking the product of these two values. So if both are +1, it is 1 into 1, 1. If one of them is -1, one is +1, it's 1 into -1, so it's -1. So this product can also take values plus or -1. Okay, those are the allowed values of the product of these two variables. Okay. Now let's complicate things a little further, and let's say that we can also, in addition to computing the products, okay, which makes sense only if for a particular instance of the game, only one of these products makes sense. Okay, because each person, if person A asks gold or silver, then this product or this product can make sense. But now B asks gold or silver, only this product will have a value. Rest are undefined. But that doesn't matter. What we are going to do is that this game is repeated a million times or 100 times or 1,000 times, whatever. And whenever each of these has a value, we record it. And in the end, you average over whatever has happened. Okay. So average is the values you get in each instance. So these values could be +1 or -1. Add them all up, however many times a particular product made sense or was defined, and divide it by the number of times it was defined. So that's the average. So we see that this number has to be a number between +1 and -1. Right. So these averages denoted by this angular brackets are some numbers between +1 and -1. Okay. So now we are going to consider a new quantity. It's a funny little quantity, which is a sum of three of them and a difference of one of the products. Okay. But again, in a particular instance of this game, this only one of these makes sense. So this whole quantity doesn't make sense. But we can always take the average of this quantity. Notice that these lines here are absolute values. So this whole quantity is always positive. Okay, it's an absolute value. Now it's easy to see that if you take a quantity whose absolute value you are taking and take its average, that's always less than the absolute value of the average. Why is that? That's because once you put the absolute value inside the average, you are always adding numbers that are positive and dividing by n. But if you put the average inside the absolute value, you are adding a bunch of things which may be positive or negative and then dividing by n and then taking the absolute value. So that number has to be always the average. Sorry, I think this is uh, other way around, right? So this is backwards, the inequality. Sorry about that. But anyway, so one is less than the other. So here I have gotten it wrong. Sorry, gotten it right. This guy is less than that guy. Okay, so this should be the other way around. So, but this average is just the absolute value of the averages of each of these quantities, right? So we have an inequality here that absolute value of the sum of these averages taken in this order with a minus sign there is always less than or equal to the average of the absolute value of S. Okay, so well and good. What can we do with this? Now let's assign possible values to these guys. Okay, and for each assignment of the probability, so I'm repeating what I said about who determines the probabilities. For each possible assignments of these quantities, let us calculate the absolute value of S. We find that the absolute value of S, irrespective of what happens, is always 2. Which means that what is the average of the absolute value of S? If every time you get 2, if you take the average, what do you get? You always again get 2. What that means is that this quantity that we wrote down has to be less than or equal to 2 always, right? This quantity has to be always less than or equal to 2 because that's what we figured out earlier through those arguments which said that average of the absolute value is greater than the absolute value of the average. Okay. So average of the absolute values is 2. So that's greater than the absolute value of the average of S, which in turn is averages constructed from the averages of these quantities. Okay. So the whole point of this is that this um, uh, inequality was written down with very little assumptions going. The only assumption that we made is that the colors of the coin and the side that which shows up are independent objective properties of the coin that are determined by what happens is determined by the dealer sitting in the middle. Okay, she decides how biased the coin may be. She decides which coin, which color coins are sent out at what frequency. So the probabilities are decided by that central agency. Okay, the coin can be heads or tails, and a gold coin can have heads and tails. A silver coin can also have heads and tails. There is no restriction that says that a gold coin cannot be heads or a silver coin cannot be tails. There is no such restriction. So the color and the side are objective properties of the uh, the coins, and the probabilities are decided by the dealer. Now, the statement that the probabilities are decided by the dealer also means that what happens after to player A or what question that player A asks cannot determine the results of what happens at player B side. Okay, so it cannot be that if player A asks for gold, silver and gets gold, then there is no way that player B cannot get tails. It cannot happen that way. See, what happens here cannot affect there, what happens there cannot affect here. The whole thing is pre-decided by the dealer, the probability. And this kind of inequality, this particular inequality, is a version of what is called the Clauser-Holt-Shimely-Holt inequality or CHSS inequality. And the Clauser that shows up here is the John Clauser who got the Nobel Prize, one third of the Nobel Prize this year. But actually, he did not really get it for this, although this plays a role. Okay, because if you say that he got it for this, then you will ask what happens to the other 3 gentlemen. But Nobel Prizes are sometimes very cruel that way. If you kind of are not alive at the time of decision, then you don't get it. Right? That has happened in this case. And also sometimes they cleverly word the whole thing so that few guys don't get it, one guy gets it. And they have their justification, but it apparently takes 50 years before you can figure out why. So, so those are some of the interesting aspects of Nobel Prizes. But right, okay. So now let's come to more interesting. physics that led to the actual Nobel Prize. So let's now replace the coins that I talked about with objects that we call as spin half quantum particles. Now, spin is an intrinsic property of particles like electrons. You will see that spin and polarization of a photon are going to be used interchangeably as we go along. But these are essentially properties that has two possible answers to the question that we ask. Just like gold or silver or heads or tails, this is a property. A spin half electron has a property named intrinsic spin, of whom we can ask, right? The question we can ask a spin half particle is, what is the component of your spin along a particular direction? Now that question is very different for a classical object like a spinning top and a quantum spin because of the following reasons. A classical spin like this has an angular momentum or spin which is represented by a vector like this. And obviously you can write down the x, y and z components of the vector. But a quantum spin, specifically sort of represented kind of very wrongly by this picture for an electron, so it's a very bad picture because electron has zero size, so you cannot really think of anything spinning if it's just a point. And then actually there's nothing spinning really. It's an intrinsic property, but it's the best you can do, or you can slightly try to do better. But the point is that you can ask it only one question regarding the component of its spin at a time. You cannot ask it questions like what is your x component of spin and y component of spin and z components of spin simultaneously, because these three properties do not exist simultaneously. In quantum mechanical languages, these properties are represented by operators which do not commute with each other. Or in the language of uncertainty principle, it says that if you know the value of one of them, your uncertainty with respect to the other components are infinite or unbounded. Therefore, only one can be known at a given time. Okay. So where does this connect to? It connects to the rules of our game in the sense that each player can ask only one of two questions. Okay. One of many questions in this case, but only one question can be asked at a time. And what's the question that the players are going to ask? They're going to ask, what is the component of your spin along a particular direction? And that direction is chosen by the player. So it's not just two questions, head or tails or gold or silver. It's any random direction. I pick this direction. I say, what's your component of spin along that direction? And a spin half particle will have only one of two possible answers. Okay. What are those answers? The answers are, so let us denote the act of measurement of the quantum spin along a direction A, vector A, as sigma A. And sigma A, if you ask the question, the electron in this case would answer one of two possibilities, h bar by 2 or minus h bar by 2. Let's ignore the h bar and all that stuff and just call the answers plus or minus 1, just as we did with the coins. Now, an interesting or significant thing about a quantum particle, unlike the coin can be either gold or silver, or it could be heads or tails. But a quantum spin or any quantum object can exist in a superposition of two different states or two or more different states. So if you denote the scenario where the spin is up along A or plus 1 along A by this state vector up arrow, and the case where it is down along A by this notation which is state down, then an arbitrary quantum system can be in a superposition of up and down. What it says is that if you ask this spin the question, are you spin up or spin down along A, with probability alpha square it will say up, with probability beta square it will say down. And since there are only two possibilities, alpha square plus beta square should sum to 1. Okay. So that's a condition of this superposition, right? So given this is what I was saying, given a state like this, measurement of a spin along A, it answers that I am in this state with probability alpha square, and simultaneously its state changes from psi to this state, or the state collapses into spin up along A. Okay, so it's like saying the coin really did not have any color when it came to you, but you ask gold or silver, it suddenly either becomes gold or silver with a certain probability. This is what happens, or this is the analog of what happens. Similarly, it can collapse into that with probability. So now you can, if you do this many times, you can compute the average of this measurement. So each time you get spin up, you get a reward of +1. So the probability of getting +1 is alpha square. So +1 times alpha square plus -1 into beta square is the average of this observable. So in this case, it's alpha square minus beta square, because the answer to sigma A acting on psi is ±1. So that's the average. So you can compute the averages also, like we did for the other case. So now we have the new scenario, right? Instead of the coins, the messengers are taking two states psi A and psi B to the player. Okay. So player A can measure her spin along one of two possible directions, which he chooses, any two. Okay, but you keep those two fixed for sake of simplicity. You can change them also. Well, let's keep two. She has chosen two directions, this one and that one. I'm going to measure either along this or along that. So that's like the choice of two questions, gold or silver or heads or tails. If I measure along this direction, it's like asking gold or silver. I can get answer +1 or -1. Similarly, if I ask the other question, I also can get +1 or -1 with certain probabilities depending on the state given. Similarly for B. Okay. So now we get back to the dealer. What is the states that she can send to the two players? Okay. A simple state she can send is where both the spins are up along some direction. Okay, that she chooses, which may not be the same as the directions that the players choose, doesn't really matter. So such a state is denoted by, say, up. That's just notation. She could be sending up down, she could be sending down up. Okay. These are well defined states in the sense that each spin has its own state. One is up, one is down, one is down, one is up, both are up, whatever along some direction. But then the same principle of superposition that we talked about says that if you apply it to the two spin system, you can create a superpositions that look like this. This is a very special superposition. Okay. Now this is very strange because, so this is called an entangled state. It's very strange if you think about it, because one of the things we said is that if you measure a spin, it will collapse into one of two possible states. So suppose I measure the first spin and it says I am spin up. Now out of these two pieces, only this piece has first spin pointing up. Therefore, the entire state must collapse into this state if the quantum collapse postulate is true. But you have not done anything to the second spin. It's also part of the game. But somehow, by measuring the first one, you have forced the second one to be in this state. Which in the game context is like saying that if player A asks gold or silver and gets an answer, she is constraining what question we can ask and what answer he can possibly get, right? So this is a consequence of entanglement, which in turn is a consequence of quantum superposition. There's nothing more to it than that. It's just quantum superposition, which is a established fact as far as 100 years of experiments go. Okay, so We cannot now jump up and say that superposition must be wrong because experiments tell you that it has to be correct. Or yet, as yet, there has not been an experiment that says that quantum superposition is not correct. And this troubled many people at the time when this consequence was realized, not probably in such stark detail, but in much more subtle detail. And Einstein was one of the guys who was really troubled by this. And in the history of things, you will see that there are long dialogues between Einstein and Bohr addressing some of these issues. Okay. So let's proceed with this quantum game. Okay. Now, instead of sending a nice state, let's up, or down, the dealer sends this state, which is also called a singlet state, to the players A and B. So now our quantity S is now written like this because player A has two choices of measurement directions, A1 and A3. Player 2 has two choices of measurement directions, B2 and B4. So A1 stands for our GH gold GS subscript, and A3 stands for our head tails subscript. Similarly, A2 and B2 and B4. Okay. So it's the same thing, slightly different notation, same exact thing. But now this is the state. You can actually compute this quantity for the case where the dealer is sending this state. And it turns out for this state, these individual averages are very simple. It is just the dot minus the dot product of the vectors A1 and B2. Okay, so that you can show. Those mathematics I'm not going into. So then you can imagine a scenario where the two directions chosen by A are these two guys, and two directions chosen by B are these two guys. The point is that this is 45 degrees, this is 45 degrees, this is 45 degrees. So the average of A1 B2 thing is cos 45, the dot product, and these are unit vectors, so which is 1 by root 2 or minus 1 by root 2. The average of A3 B2, that is also cos 45, which is 1 by root 2. A3 B4 is also plus or minus 1 by root 2, minus 1 by root 2, let's say. But this is something else, right? That will be a 1 by root 2 with the opposite side. So when you put 1 by root 2, 1 by root 2, 1 by root 2 and minus 1 by root 2 here, you get 4 times 1 by root 2. 4 times 1 by root 2 is 2 root 2. So this quantity with absolute value is actually 2 root 2, which is greater than the limit we put from CHSS inequality, where we said that for any local realistic theory like classical mechanics, this quantity has to be less than 2. So we see that quantum mechanics violates this inequality or CHSS inequality, which is a special case of what is called Bell's inequalities. Okay, that's a more broader class because the motivation for Bell to develop this whole thing, Bell got his Nobel Prize much earlier, was Einstein's discussion, Einstein and others' discussion saying that entanglement represents spooky action in the distance. How can something that happens here immediately affect something that happens over there? Something is acausal, something is wrong. Therefore, he said that quantum mechanics must be a incomplete theory. Not just he, many people said that quantum mechanics is an incomplete theory which must be supplanted by a correct theory later. Or a different way of saying is that there are some variables associated with quantum systems which you do not know about now, but if you know them, you can make sense of what's happening. So those things are called hidden variables. What Bell showed is that any theory, whatever it may be, if it has, even if you allow for hidden variables, as long as those hidden variables are local, in the sense that the value of the hidden variable does not change abruptly if you do something to one side. The hidden variable should not change, variable value should not change abruptly on the other side. As long as you make that very broad assumption, there are always inequalities of this kind which you can find. And if experimentally measure these quantities, these averages, those are things you can measure in an experiment. You measure those experimentally, add them up, and you get a number that violates this inequality, then no matter what, those results cannot have come from a local realistic theory without hidden variables as Einstein hoped for, or Einstein and others hoped for. There may be a super theory that supplements or supplants quantum mechanics, but it still cannot be one based on local hidden variables. It can be non-local hidden variables, but that doesn't really help the situation. It has the same problems that Einstein thought of as spooky action at a distance. So the violation of this means that quantum mechanics is not a local hidden variable theory. So Nobel Prize in 2022, right, is for Alain Aspect, John Clauser, and Anton Seligman, each have conducted groundbreaking experiment. That's why I said Clauser did not get it for writing down the CHSH inequality, but for actually doing the experiment that shows that measured those averages and showed that when you add them up, it actually gives you a number greater than 2 in that case. The exact form they used is slightly different. Uh, uh, they had to get some number greater than 0. It's just like taking that 2 to the left hand side and saying it is greater than 0 or less than 0 or whatever. And that's how they got the whole thing. This is the image from the Nobel uh, committee trying desperately to capture the spookiness of entanglement with these, like, I don't know what those are, but it also illustrates how difficult it is to actually conceptualize this idea or visualize this idea using our classical notions. But like Einstein himself said, common sense is a bunch of prejudices that are sort of forced onto us by the time we are 15. So sometimes it's good to get rid of those things, right? So this is the Nobel citation. So just a quick rundown of what Clauser did. When Clauser arrived at UC Berkeley as a postdoc in '67, he was working on some atomic physics before that. He noticed that there were two experiments. There was an experiment by Carl Kocher and Eugene Cummins, which um, um, produced for Clauser entangled photons. I'm not going into detail why it's entangled or how they think it is, why they think it's an entangled photon, but various reasons are there. Now, entangled photons, the property that you are studying, like the spin, is a polarization of the photon. It is a very simple, similar thing. Okay, it behaves exactly the same way, more or less. But photons are at that time at least easier to work with because they are not disturbed by their environment too much. And Clauser and Friedman essentially repurposed and improved the Kocher-Cummins setup to demonstrate violation of Bell's inequality. It's from again the Nobel citation, a schematic of their little uh, um, experiment. The crucial part here are these two polarizers. Okay, these polarizers are like the decisions that the two parties A and B take as to which direction do I measure. So the scheme, what I want to highlight here is that the scheme is such that this polarizer has to be set before the calcium atoms come here and produce through the Kocher-Cummins mechanism the entangled photons. Because each time changing the direction of the polarizer is a difficult task. It takes time. So you have to set it, do the experiment, measure many times where both photons come through and do a coincidence count, etc., and capture the average, change the polarizers to the other two settings, do whatever you want, find the average, and so on, and then add the averages, subtract them, and all that, take absolute value to get the violation. Okay. But this point that the polarizer has to be set ahead of time created some hardcore fans of Einstein and company to say that, this actually provides a loophole for hidden variables to enter back into the theory. Because when you set the polarizer, something has happened which can causally affect what photons come out of the, what kind of state of the photons come out of the calcium atoms. So actually, you should decide on the direction of measurements after the photons are created, but before they hit the photomultiplier tube. And this distance was around 6 meters, which meant that you have to change the polarizer in a matter of less than 20 nanoseconds. Okay. And that's where Alan Aspect's experiments come in. He did a sequence of experiments in the 80s, which even I remember when it was first announced. Some of the people, my uncle and others, talking about it. I was probably too small to remember the details, but even then it was big news that Aspect had done these experiments. And again, like Nishana was pointing out, the technology was very different. These are things now people use routinely in optics labs, what I call acousto-optical modulators, were kind of used to, the photons are produced, and in that split second before they get to the photodetectors, these acousto-optical modulators change to mirrors so that it is sent into one of two possible paths. Okay, and in each path, the polarizer setting is different. So effectively, which polarizer setting to use is decided while the photons are in flight, so that the predecision cannot affect the photons at the time of their creation. So that's the locality loophole. Okay, so that was closed kind of convincingly by Aspect, and people are now doing more things, right? China, actually, I was talking to one of the leaders in this field, Genwei Fan, 2 years back. They were planning to do this with one actual person sitting on the moon, okay, and another person on the earth with a satellite sending the photons at a predetermined time, and between the time of creation of the photon and the detection, actual humans decide the polarizer, not acousto-optical modulators and all that. Because you can say that, okay, even the acousto-optical modulator setting was pre-decided on a computer, it's going to flip or not. Right? Will that create a local hidden variable? Okay. So avoid that by actual humans deciding the polarizer setting, except that you need a time for humans to react. So put one guy on the moon to do this experiment. They're actually planning this. Zyliger did an experiment where the direction was actually correlated with light coming from distant stars, which are presumably uncorrelated. Depending on the nature of the light from two different stars, right, the polarizer setting was changed. So he did an experiment, but he did a lot of other experiments, including using entanglement to do what is called quantum teleportation. So, just to sum up, Nobel Prize in 2022 recognizes the rise of quantum technologies, right? Which is quantum physics coming out of the textbook and the lab into actually applied regime. And things like entanglement and superposition are not only known to be now real, nobody questions it except some hardcore hidden variable guys, but it can actually be used to do things that you cannot normally do. Right? So these quantities, these concepts become resources that one can use to do computing, to do communication, to do sensing, to do and other uses in ways that you cannot do with classical physics. So this is just a picture of one of the quantum computers with a few qubits. These are other approaches to computing. And then this is quantum cryptography or key distribution across satellites, which is unconditionally secure, again using entanglement, superposition, and various other notions. And this is actual results from the LIGO gravitational wave interferometer, which got a lot of attention a few years back and got the Nobel Prize last year. It was also facilitated by being able to use the quantum features of light to improve the sensing accuracy. So quantum technologies really played a big role there. Right? And so it's an exciting frontier. And thank you. I just want to put this up for just to underline why Zeilinger deserves the Nobel Prize. Because among all these other things, teleportation and all that, he even did an experiment where he showed that these buckyballs with 60 atoms thrown at a knife edge one at a time actually leads to a diffraction pattern. So which means that a molecule, not photon, a molecule as big as this has wave-like properties as predicted by quantum mechanics. It shows diffraction, and that too one at a time. It is not a bunch of them. One at a time they are sent, and it ends up showing a diffraction pattern. Okay, so thank you for your attention. So, if there are any questions?
We have taken entangled states.
Right.
Yes. And the current interpretation of quantum mechanics that we are taking, that we use, that is Copenhagen interpretation.
Among other things, there are all sorts of interpretations. But
yes, but we have taken as an assumption that determinism is not there, but locality is there.
no, not locality, causality is there. That is a slightly different statement because the consequences of entanglement cannot be used to send a signal or send any information faster than the speed of light. And that comes in through a very subtle way. It's not as transparent as just thinking about entangled states. How does it stop? Uh, or to see, for example, uh, if you have two faraway parties and you share an entangled state, and I want to communicate yes or no. Okay. But if I take that entangled state that I wrote down, up, down, plus, down, up, I know that if I get a measurement result up here, the other one is down. Okay. And if I get it down here, the other one is up. So it cannot be actually used to communicate yes or no because when I measure, I don't know what I'm going to get. Okay. Because if I say that if your state is down, it means I got an up and therefore it's a yes. And if your state is up and I got a down, that means no. But I don't know what I'm going to get. So I do an experiment, I get something. So if I wanted to communicate a yes, I have to get a spin up here. But I don't know what I get. So if I want to communicate what happened, I have to actually tell the other guy this is what I got. But that goes only at the speed of light. But you can do other things. I can say that if I want to say yes, I will measure along the z axis. If I want to say no, I will measure along x axis. Okay. Then depending on what measurement result I got, the state over there changes. But again, the problem is that there is no way of detecting what I did here without me actually saying. So causality is needed. It is affected, but no communication is happening.
Yeah, even with space light,
Even if it's space light, non-relativistic quantum mechanics tells you that it has to be affected, and there is nothing wrong with it. You can correct it with the relativistic quantum mechanics, which becomes quantum field theory, which will tell you how these things propagate. Okay, but that's not really needed because causality is still preserved, right? So in a very subtle manner. And this 2 root 2 is a very important number because if that violation is greater than 2 root 2, you can show that quantum mechanics is not causal. So nature is working at that limit. It is non-local, it has all kinds of funny properties that are not classical, but it's still causal. It is violating Bayes inequality by exactly 2 root 2, not 2 root 2 plus 0.00. Because if you do that, then you can show that the theory can be used for signaling faster than light. So therefore, relativity is still satisfied, causality is still satisfied, but it's still not classical, it is not local realistic. Yeah.
Sir, thank you for the talk. The question is that since IISER removed this locality.
Well, pushed it one step back in the sense that what the signals coded into the acoustic optical modulator, if it affects the creation of the, because the AOMs are going to be controlled by computers. You have to tell the computer ahead of time what to do. It will do the switching very fast while the photons are at in flight, right? But you have to do something before to actually tell you to do. So people say, okay, what if that affect? Okay. So so this loophole is not completely closed, but it became Alan Aspect's main contribution is that it started becoming ridiculous to try and reopen the loophole. So people are forced to accept, or a good majority of people are forced to accept that entanglement is the way things are.
And as you told that triangulated that cosmic areas in which the
Light from stars are used to.
my question is that okay, by that passage of time, you've been able to kind of close or like, come close to eradicating these loopholes, but that does not kind of affirm that there's not a possibility of any sort of hidden variables, which maybe the nature does not want us to have an access to.
No, but as long as once you close all the loopholes, Bell's theorem tells you that there cannot be a local hidden variable thing. Because it starts with no assumptions. It only says local assumption. Hidden variable. So only way for it to come back is through these loopholes, which are getting increasingly far-fetched. So at some point you will be able to close it. Now that doesn't mean that quantum mechanics is the ultimate theory of everything. There may be regimes in terms of size, scale, or whatnot, where another theory comes up. But that is also not expected to be local realistic. Because if it is, you will not see, you cannot derive Bell's inequality violations from that underlying thing. Okay.
So the delayed choice quantum eraser experiment has was recently thought to destroy causality as we thought it, like or create a causality paradox. So
little bit of a paradox if you want to think about it. So the delayed choice experiment, right, is a little bit of a funny thing which has to be really analyzed in detail to understand that causality is still preserved. It looks like it is not. See, the delay choice in simple terms is the following. We know that if you've got interference, double slit interference, right? If you close one of the slits or actually look at one of the slits and see which way the photon or the particle went, then the interference pattern is destroyed. So the delayed choice essentially works out to the statement that, okay, I'm going to look at which slit the photon goes to, okay? But I will look at it only after the photon has had time to hit the screen, okay, not before it hits the screen. So that's what it means by delayed choice. I choose whether to look at which way the photon went or not. Actually, after the interval of time it would take for the photon to hit the screen. Therefore, can that affect whether I see an interference pattern or no interference pattern? Okay, because I did not measure it in time for it to know that I have measured. Because I have delayed my choice to measure or not. It turns out if you analyze it carefully, you will find that it's perfectly causal. That's because actually there is a third party involved. Because this delayed choice is facilitated by the presence of a of another quantum system, which you can choose to look at later or not, and then from it infer which way the photon went. So if you analyze it, the flow of information in fact is causal and linear, although the sequence of events looks very acausal because something that you did later is affecting something that should have happened before. So it looks like it is affecting the past.
So essentially, the Wheeler's paradox is also perfectly possible.
Yeah, the information flow is always forward, but the sequence of events when translated to normal language looks acausal. But very often it's a problem with normal language and not with the physics of it. I don't know how we'll do it. I'm doing for time, so you have to decide when to stop.
So, sir, when you were explaining the acousto modulator, you said that there's a hidden variable in the code, I guess. Can the same argument be said? It can be said for the moon experiment that you suggested.
I guess then that means that the two observers are somehow connected. Their thoughts are somehow, or their decisions are somehow connected ahead of time. So you can do that, but then that means that also has philosophical consequences, including there's no free will and all that, because what you choose is contingent on what I choose, and vice versa. Right? So these are philosophy. So it goes into philosophical issues, which inevitably it does, right? Because the question of who collapses the wave function, whether Schrodinger's cat can collapse its own wave function, immediately gets into the realms of philosophy, neurology, whatnot, and all that. But those are interesting questions. At least some questions should be there for you guys to answer, right? Because
And regarding the entanglement state that you said, half into up down minus down. Can you also create a entangled state which has a different probability for both states? So
yeah,
by
I
alpha
just
is 90% or something.
I just took the special case where our alpha and beta are both 1 by root 2. That's just because that makes the remaining calculation of those averages, etc., simple. If I took another state, those averages are not A dot B. It is some complicated function which I don't want to draw out here.
So the system can be sort of optimized to actually create a proper communication method. Say I set my alpha square for the first state to be say 98% or something.
But
So
you,
I have a high chance of getting that first state.
yeah, but the thing is that you will find that anything away from the singlet state, the degree of violation of Bell's inequality starts decreasing. Until when alpha becomes 100%, there is no violation because it becomes a classical state. So usually what's done is that it's the reverse. The quantumness of a state is sort of characterized by the degree of violation of the Bell's inequality or Bell type inequality.
Thanks.
Okay, thank you.
Thank you, Professor Shaji, for the exciting talk. So we have refreshments outside. So the break would be for 10 minutes. And after that, we'll have the talk. Uh, yes, doc, from Dr. Sebastian, first time from Hungary. All of you are requested to come back after 10 minutes. It's just a short break.
If you want to ace your paper, download Grammarly. Are you? Me? Yeah, see you in 3 months.
Welcome back, everyone. We would like to welcome our Honorable Director, Professor J. and invite him to address the students.
Okay, calibrators. I am not here Can you bring down the volume? No, I don't. I want to ask all of you guys, what time was this supposed to be started today? 9:15. Is a science institution. Is a science institution, right? How often do we have this? Once a year, right? It's a once a year. If your science students, is there that passion? It's an exclusive organization for science education. In a science education, if you do not have some scientific activity taken forward by yourselves as science students, the ANVESHA is yours. Every department has its own activities. We have students belonging to different disciplines. Once a year, there are a few enthusiastic students put up a proposal. Sir, we would like to do under the ANVESHA Science Club some annual event. Eminent people, they've done their job. I would like to, applaud these guys. And bunch of you and the entire student community, I don't know, you should get this message across. I'm really, really hurt. What do I get by shouting at you? Do you get anything? Do I get anything? I only become bad guy for you if I shout at you. I don't give a damn good. I'm here to create some culture, bring some kind of visibility that allows us to be seen as a respectable organization in the country and abroad. If our organization and the institute earns its reputation, the constituents, the people that belong to this organization automatically get recognized. It is you. At the end of the day, the reputation that the institution earns percolates down to you. You are going to be the beneficiaries, not me. For me, it doesn't matter. I want my reputation. There's nothing that I have to prove to the society today. No, I am worth something. I've done my science. I've got the laurels, pretty much everything in this country. And I'm also heading this institution. There's nothing at stake for me. I don't need anything more for as an academician. But my intent is, as an academician, to give some structure, shape, visibility. I address not you, you guys, the guys who are hiding in the hostels. For one day, they cannot come out and be part of the scientific activity. Then what are they here for in this institution? What have they come here for? If not for science, if not for upgrading themselves, if not for exposing themselves and learning something more, if not for the wisdom to gain from people that are invited into the campus. Now we spend money on them. There are going to be people that are coming. We approved a few lakhs as part of this scientific activity. If there are only about handful, then why are we spending the taxpayers' money for? Tomorrow, your group leaders, student leaders come to me, sir, support us for this and that. I said, get lost. I support the money of taxpayers. For whom? If you bring some people, I was really shocked. We have an eminent person from RBI to speak to tell us about why the Nobel Prize in Economic Sciences has gone today for three gentlemen. I was planning to come myself. It's not my domain. As an elite member, members of an elite institution, where supposedly high quality education is provided, we should be informed about developments in other domains as well, not being so passive, not just growing up as narrow minded specialists. When we graduate, we should know a bit of everything else around, right? Huh? If I'm a chemist, should I be only a chemist? If I'm a biologist, should I know only about biology but nothing else around? Then that doesn't make you a good citizen and that doesn't make you a good scientist. And more so in 2020 NEP, which demands that you submerge down your activity that the scientists have been traditionally pursuing in silos. We should move out of our boundaries. Allow ourselves to be exposed to other things, which is what ISERs are meant for. First 2 years being very, very common, so that the fundamentals of everything is known to you. You grow up as a scientist with no barriers to jump into any area that appeals to your heart and carve a niche for yourself. A scientific activity, Anvesha, a science festival, not for me. Sad it is that you have to be basically flushed out from your hostels to bring some respect for the vigilance that we have here. As a scientist, basically, of some national recognition giving a talk. Shame also on part of the faculty. I think you should tell your colleagues that there are not even 20 faculty here, and we demand the students. The culture that has gone awry here. Understand? And this is not what I would like to see. Somebody need not come to your hostels and tell you guys there are lectures going on. Come on. No, forcibly nothing can be taught. It has to be inherently be there in you, in your inner soul. No, what am I here for? Should I be so narrow-minded? Is that if there are activities, if there is something about basically Nobel laureates, Nobel prizes in the current year, should I not know? If the institution is celebrating as a whole, am I not one scientist? Don't I belong to this family? If I am one, why can't I be part of the group? Should I tell you about this? I want to see a change in the culture. Get this message across to all your friends. Okay? Next time, no, I'm not inaugurating this. I've told them that I'm only going to admonish you guys. Let this message be out there across to all your friends. Don't insult organization, which is keen to help you, which is keen to push you to a higher level, which is keen to expose you to developments in all disciplines. If somebody is out there to give, you should not suppress those instincts. If somebody is willing to help you, you should not push such a system away. You should help yourselves. You get it? Okay. Get this message across to all your community. Okay. So I think as part of the Anvesha, I think I must basically, you know, applaud these guys. Let's applaud these guys. They have they have put in they have put in their effort. It also means even a few faculty like Dr. Jishi, Dr. Nisha, and a few others have invested their time in putting together this particular program. You know, and developing the website and advertising is a waste of energy. You should motivate your friends. You should basically stand by them. Solidarity is very important. They are wasting their time, not for themselves, for all of you. So get this message across. Don't do this next time. I should be willing to spend, if I see good participation, my student community is really, if I feel, oh, ours is a different bunch of guys here. They are very enthusiastic. They are here out here to learn. Then I'll feel motivated tomorrow to support any activity for you. If I'm spending money, it only goes down the Ganges. If that is the perception I get, I will be demotivated. You will get nothing. Okay? I would like to see a better response. Everything that is done is for you. You are the beneficiaries. We don't need anything. Okay? I think a lot of science, activities. I hope that you guys at least take my word seriously and help yourselves and make this ANVESHA, the science club, a great success. Before I, wind up, I wanted to tell you a few things, but unfortunately, I'll defer that to some other occasion. There are a lot of things happening in this country. I don't know how many of you know. There's something called as a KDISC, Kerala Development of Innovation Strategic Council. Amongst all states that I know, Kerala is really, really aggressive, has been aggressive in promoting innovation ecosystem. And in fact, they have come up with what is called, as I told you, Young Innovators Program, or what they call as a YIP. It's basically to provide solutions to real life problems that are there everywhere. If people can come up with, they can submit their proposals to the Kerala state government, and they provide a seed money if your proposals are exciting. So, in other words, everything comes down to innovation. There cannot be anything without science. A technology builds on science. If you don't have a scientific invention, you don't have technology. When you have scientific innovation, then you seek resort to engineers, take their help, come up with a design, prototype, translate that into a product. The product then goes on to become useful to the society. So, in other words, a product pipeline, if you see, everything comes back to scientific innovation. The science with engineers translates into technology, technology then becomes a product becomes relevant to society, society remains much better, and then the questions are raised back to the scientific innovations. It's a loop where the science is a rock bed. Technology won't. If scientifically you want to innovate it better, then ask the technologists to sort of improvise. The product gets better and better. A simple example is a cell phone. 20 years back, we could barely speak. 30 years back, we only had a rotary dialing system. Today, we virtually, really look at the person and speak. Miniaturization. This happened because scientific inventions, engineers coming into the picture, technological development, society posing questions. No, we don't want big displays, we want miniaturization but higher resolution. Then you have cathode ray tubes got displaced. Then you have TFT basically gone into the wind. Now you have LED technology. Now we are looking at a QLED. You understand? It's all based on science, right? Technology comes later. The inventions happen in our laboratories. No science can prosper without science. And it's very appropriate that the government has been well thought out in creating the scientific institutions. You might wonder what the hell I do in the laboratory is going to be of use tomorrow. No. Simple example is all of you have studied 10 plus 2. If we did not bother to know carbocation, today we would not have measure for how good the fuel is. Octane number. Where does it come into picture? Somebody worried about carbocation stability. Where when you cleave, you have a stability, and that becomes a way for fuel quality. If somebody did not bother about the carbocation, which has no relevance to fuel, he never even imagined like this. You don't know what you do today becomes important 20 years later. If you're talking about the LEDs that we are used to with cell phones, 1970s and 80s, people only were bothered about see whether there can be conductivity in organic materials. Can we see, and by conductivity you can generate excited states. Forget about the emission. You can see a little light. And that little light today is a luminance of highest order, which has displaced even the everyday batteries for light. Nobody uses them now. So don't worry. What we do today may be relevant after 20 years, but scientific activity has to go on. Right? Now, increasingly questions are being asked, particularly from the young minds. This is what I want to tell you. I wanted to tell you. There's so much being demanded. Advanced minds like ours are saturated. We cannot identify the problem. But young minds, because you are not exposed to anything, everything should be a question to you. Everything becomes a question to you if you spare your little mind without your earphones plugged in and your eyes basically closed into the cell phones. If you observe the world outside, you will identify the problems. But unfortunately, younger generation is lost in the cell phones. Throw them out, observe the life around you incisively, is what I want to tell you. Identify the problems. There are plenty around at every stage. Allow your imagination to stretch as to how you could provide solution. Come together under one roof. Engage in discussions with your friends. Debate on, hammer it out on problems that are faced. And I'm sure there are going to be solutions. Such are the solutions, for example, that KDSK is looking for. Innovation challenges are plenty now across the country and in the global scene. You come up with one innovation, I think your life is worth it. I think we had Balagopal Chandrasekhar, right? Story, who was an IAS officer who stepped into Sri Chitra Tirunam, got struck by a scientific innovation that he decided to kick his job, developed an industry that feeds now the world with more than 35% of the demand for blood storage bags. And he has declared about 25 fellowships for us today. Ordinary men who had no connection to the science, right? We had no connection to the science. But at least we are practicing scientists. Observe, identify, stretch your imagination. Okay? Contribute to the society. Thank you.
We are deeply sorry for the inconvenience caused and plan to do better further. I would like to invite Dr. Trishan, present a memento to the dead. We will now go on with our another lecture series. I would like to call upon Dr. Alice Sebastian. Dr. Alice Sebastian is a well-decorated economist and an assistant advisor in the Department of Economic and Policy Research of Reserve Bank of India. She is currently based in Kochi office, Kerala, and has immense knowledge in general studies, labor economics, and educated unemployment. She has lately begun to explore public and monetary economics in depth. Having obtained a PhD from Jawaharlal Nehru University, she has written several articles on inflation, exchange rate volatility, unemployment, etc. We welcome you, ma'am.
Thank you for inviting me for this lecture. I know talking economics in a science institute is going to be challenging. So I'll try to make it simple and useful so that you feel you get interested and stay engaged till the end. So this is Nobel Memorial Prize in Economics. Recognized the huge importance of banking and finance in modern macroeconomics. So the winners this year, Ben Bernanke, Douglas Diamond, and Philip Dubik. These three economists, they pioneered two distinct but ultimately related themes of research on the role of banks in modern economics. Diamond and Dubik co-authored a fundamental paper in 1983. Nobel Prize in Economic Sciences uh, recognize the importance of banking and finance in modern economy. So the winners this time was Ben Bernanke, Douglas Diamond, and Philip Dewey. Among them, I guess probably some of you must be familiar with the name Ben Bernanke because he was also the chairman of US Federal Reserve, that's the Reserve Bank of US. So they basically pioneered two distinct but ultimately related themes of research on the role of banks in modern economics. And Diamond and Dewey, they co-authored a fundamental paper in 1983 on the logic underlying the existence of banks in modern economy and the inherent risk that it entails. And Bernanke, he worked independently from the other two and published seminal paper that same year on the role of banks in during the Great Depression and well beyond what was the role of the bank in prolonging the Great Depression. So these two seminal papers won the Nobel Memorial Prize for Economics this year. Basically, from my personal perspective, I am particularly delighted about this year's prize because this was the first time that research in banking was recognized in Nobel Prize in Economics. In fact, the last time a Nobel was won for anything to do with money or monetary economics was in 1976 when the great Milton Friedman was awarded Nobel Prize for his research in monetary economics. So since 1976, there has been many Nobel Prize in, field related to banking or monetary economics. So it was high time, and the choice was also great, which I will later tell you the reason. So first, what I will do is I will first talk about the contributions of Diamond Douglas and Philip Dewey because they work together and they work together on similar issues. And then I will shift the focus on Ben Bernanke's contributions. And before bringing them together as part of the general theme that was outlined by this year's Nobel Prize Committee. And in the third part of my talk, I will talk about how the modern view of banking is actually posing some challenge to the work done by these Nobel laureates. So let me start by showing you a simplified balance sheet of a commercial bank. Those who are from commerce or economics background, they might be familiar with a balance sheet of a commercial bank. So what does basically balance sheet shows? It shows the asset side and the liability side. So bank essentially collects funds from some people and deploys these funds in a variety of ways and earns profit. So this is basically what the bank does as a commercial entity. Now on the liability side and liabilities and capital side, you see two components. What is capital? So what is the capital for a bank? Capital is the money put in by the owners of the bank. That's the initial capital of the bank. For example, if it is a public sector bank, means like it's a bank owned by government, then it is the initial capital investment made by the government if the bank forms part of the capital of the government. Now, what is deposit? Why is deposit a liability? Because you have to give the money back to the people who deposited the money in the bank. So deposit is the form part of the liabilities of the bank. There could be other sources of funds for banks, like banks can take loans from other banks. That can also be part of the liability side. Now, coming to the asset side. Now, asset side shows what do the banks do with the fund raised on the liability side. The asset side, you see an important item called reserves, which is basically the money the bank has to keep with the central bank, which is in India's case, it's the Reserve Bank of India. So currently the CRR is 4.5%. What does that mean? It means for every 100 rupees that bank takes as deposit, it has to keep 4 rupee 50 paise with the Reserve Bank as a reserve money. That is the CRR ratio. Now, the second category that you see in the asset side of the bank is the loan. Now, why loan is an asset for the bank? Because it earns banks an income in form of interest rate or in form of interest. And bank can give a variety of loans as part of its portfolio. Now, the other item that is left on the asset side is the other assets. Now, what are these other assets? It can be like bank can buy bond, it can have it can invest in shares, it can buy gold. So these assets form part of the other assets in the bank's balance sheet. Now, the basic fundamental about the balance sheet is that it has to balance. That is, the asset side has to balance with the liability side. Now, having this fundamental in knowing this fundamental, now coming to the important question: what is the bank created for? What's the basic function of the bank? Now, it is traditionally believed that banks exist as a financial intermediary. That is, it collects deposits and converts it into loans. That is believed to be the traditional function of a bank. Now, here is where the contribution of Diamond and Dewey comes. So, their research basically has took on this task of articulating a clear reasoning behind the existence of bank in modern economy, while also in that process they highlighted what is the potential risk underlying in the existence of bank, in the functioning of the bank. So these two are the path-breaking papers cited by Nobel Prize Committee by awarding the Nobel Prize to these two economists. So what do these two papers say? First of all, they talk about the role of banks. So what do banks do? So to understand what banks do in the modern economy, we have to think about a world without banks. Suppose we live in a society where there is no banks. So what do we do with your savings? Say I have some surplus cash which I wanted to invest somewhere and I wanted it to grow. Like I want to save my savings so that I can, use it as a future asset. Suppose I live in a world without banks, then I myself has to find a borrower. I can find a company who is interested in investing my money to build a factory, or I can lend my money to a household who is interested in buying a house. So I have to do this on my own. Now, what is the problem of this direct borrowing and lending? Because this is a very difficult task because these borrowers and lenders have very different needs. Now, what are savers looking for? Savers are looking for opportunity to deposit their money so they can withdraw it anytime. So they basically wanted liquidity. So if I hand over my money to a company, now company is not going to give me back my money in next 10 or 15 years because they invest in projects which takes time. They have to build the factory, they have to produce goods, they have to sell it, and then the cash flow starts coming, and then only they will repay my money. So I don't have the option to withdraw my deposits which I have invested in a company. But savers want to park their money for a short period, for a year or so. So this is a problem called maturity mismatch. Now, I hope you understood what exactly that means. Like I, as a saver, I'm looking for short-term maturity, while as a borrower, I'm not looking for long-term maturity loans. Second mismatch that if we go for a direct lending and borrowing is the size mismatch. Individually, I have small amounts of savings. Like I have 20,000 rupees with me. You may have 50,000 rupees. But a borrower, like a company, wants a 1 crore or 2 crore to invest. So how do we, get such small amounts from individual savers? So this is a size mismatch. And then there is something called a risk mismatch. What is that? Now, savers want their money to be safe. They wanted to invest in safe investments. But very nature of businesses are risky projects, and firms are looking for high risk projects which can give them high returns. So companies are looking for risky projects while savers are looking for safe investment opportunities. So there is a risk mismatch there. Now, these problems of mismatches by playing the role of an intermediary. So these are the three important functions that banks do. One is maturity transformation, which is what do the banks do for maturity transformation? So banks collects small amounts of deposit from each one of us, which could be a 1 year or 2 year fixed deposits, and banks convert those small amounts of deposit into long-term loans, which is like 10-year or 20-year loan. So this is the maturity transformation that banks do. We won't be able to do this ourselves. Now, second role that banks do is the size transformation. Now, bank is collecting small deposits and pooling them together and giving large size loans. So this is something that only bank can do. Individually, if I try to borrow and lend it to companies or households, I won't be able to do this size transformation. And the third thing that banks do is the risk transformation. Bank is keeping my money safe, and at the same time, bank is giving out risky loans to borrowers. So this is the risk transformation that banks do. Now, here is where the contribution of Diamond and Dewey comes. In their 1984 paper, they actually shows that if individuals like us, if we try to lend our money to borrowers, we won't be able to monitor what the borrowers do with our money. It is going to be highly costly and difficult for individuals to monitor the borrowers. Now, what do banks do? Banks, we as borrowers delegate this role of monitoring to the banks, and on behalf of the borrowers, banks monitor the activity of the lenders. Now, this is how banks do the risk transformation. Now, when banks do these functions, when they do the maturity transformation, when they do the size transformation, risk transformation, it has got its own inherent problems. Now, this financial intermediation of collecting the deposits and pooling the deposits together and giving out large and risky loans, this generates the kind of risk which is called the bank run, or a bank collapse, or a bank failure. So the famous Diamond-Dewey theoretical model actually explains this, how the financial intermediation of bank generates the risk of bank run. So what I will do first is I will tell you the story of this model, and then if you understand the story, that is well enough. And then I will go into little details by giving you a simple numerical example of how this model works. Now, suppose say depositors have some surplus funds. They want to save this money somewhere. At the same time, they wanted access to liquidity. That is, they want their money whenever they want. Now, this is a problem that I said earlier. It's a liquidity mismatch. So the deposits are liquid, but loans are illiquid, which means loans cannot be called back, but deposits can be withdrawn at any time. So when there is a liquidity mismatch, banks step in and banks provide what is called a liquidity insurance. What is that? It is a guarantee that bank is giving you a depositor that don't worry, give me your money. I will make loans with it for 10 or 15 year long loans, and these loans are risky, of course. There may be a default, but I give you a guarantee that whenever you want your money back, I will give you that money back. That is the liquidity insurance that banks are giving. And it's not just the liquidity insurance, you are getting your money back with interest. So this is very important. If bank is simply going to give me back my initial capital, I will keep that money with myself, right? I'm interested in investing in bank because one, my money will be safe, and second, the money will earn me a return, and third, I can withdraw it at any time. So this is the liquidity insurance provided by banks. Now, there is an inherent problem with this liquidity insurance. What is the problem? You see, when you go to the bank and ask for your money back, bank will give you your money back, but then that is not actually your money. Your money has been given to somebody as a long-term loan. Bank may be having some cash in its vault, which is giving you as your money when you withdraw your deposit. Now imagine thousands and thousands of depositors come at the same time and ask for the demand for their money back. Do you think any bank in the world can meet such kind of a pressure? No bank in the world holds so much of cash with them that they can actually meet the withdrawal pressure of a large number of depositors coming at the same time. Now, what will banks do in such a circumstance? It will simply close its shutters because it doesn't have money to give the depositors, cannot promise the guarantee made to the depositors. It is called a bank run or a bank failure. So a bank run is when a bank shuts down or collapses because it cannot promise the guarantee that it will give to depositors. So how does a bank creates liquidity insurance to the depositors, and how does that creates the risk of a bank run? This is exactly what Diamond Unique shows in their model. Now, I'll give you a simple illustration which essentially gives you the gist of the model. Suppose you invest 1 rupee today in some asset. Now, this 1 rupee is still worth 1 rupee next year because, as you know, when you invest a 1 rupee in a company, the company has to build a factory, it has to produce things, it has to sell goods, and then only the cash flow will start coming. Then only your money will grow. So in time period t equal to 0, which t stands for time period, and when it is time period 0 means current time. So right now, if I invest rupee 1, it remains rupee 1 in time period t equal to 1. Now, at the end of 2 years, that is when time period 2, if I am patient and I wait, then my money will grow. Then what happens? Then the company will start producing goods, it will start earning profit, and then your money grows. And let's assume that the money will get doubled in 2 years. That is, in time period 2, if I wait for 2 years, then my money gets doubled. Of course, in real life, money doesn't get doubled in 2 years. So don't fall for such money doubling schemes, which we commonly come across. So let's imagine that there are some patient investors who are willing to wait. Let's call them type 2 investors. So type 2 investors are the investors who are willing to wait till time period 2 for their money to grow. And but there could be some other investors who are impatient and who want their money back at time period t equal to 1. So it could be some emergency in the family, some health catastrophe that they had to take their money back at the end of first year. And let's call them type 1 investors. So what do bank do now? Bank has guaranteed all investors that whenever they want their money back, they will get it back with interest, right? So what bank can do right now is it can give these type 1 investors their deposit plus an interest rate. So is it better to invest in a company directly than invest in a bank? Now, if you invest in a company, as I said, you won't get your money back in say next 10 or 15 years. But if you invest through bank, then even if you want your money back right now, you can get it back. That is why people prefer to invest in banks. But the only problem here is in the initial period when this investment starts and when bank collects the deposits, this information is uncertain, like how many investors will turn out to be type 1, how many will turn out to be type 2. That's the inherent risk in banking. Now, let me give you an example, a numerical example where a bank has 100 depositors. So, bank has collected 1 rupee each from this 100 depositors. So, bank has got 100 rupee worth deposit. Now, bank has pooled in this money and has given it as a loan to a company. Now, at T1, rupees 100 has not grown. It is still rupees 100. Now, at the end of first year, suppose that 25 out of these 100 depositors turn out to be type 1 depositors. And they come to the bank and ask for their money back. Now, bank can give each of these 25 depositors 1 rupee 28 paise each. That is the interest that bank has promised. Now, how does bank do it? Bank has already invested this 100 rupees in the company. Now, what bank will do is bank will pay each of these 25 people 25 times 1.28, that is 32 rupees. And accordingly, bank's assets will come down from 100 minus 32, that is 68 rupees. Now, bank is left with 68 rupees for the next 1 year. Now, at the end of 2 years, this 68 rupees will double. And then the bank can pay out the remaining 75 depositors 2 times of 68 rupees, that is 68 into multiplied by 2 divided by 75, so that each depositor will get 1 rupee 181 paise. They are happy because if they have invested, so of course you can say that if they have invested directly in the company, they would have got 2 rupees. Now they got only 1 rupee 81 paise, but still they are happy because it's anyway better than, gives them higher liquidity. So because there was a sudden emergency and there was a need at the end of 1 year, some people withdrew it and got it 1 rupee 28 paise. And because of the attraction of liquidity, people are still willing to invest in a bank rather than investing directly in the company. Now, so far so good, because you have only 25 depositors who turned out to be type 1 investors. Suppose say instead of 25 people, if more people start demanding their money back, how far a bank can stand? Suppose this number increases to 26, 27, 30. What will bank do? This model is fine as long as not too many people demand their deposits back. Suppose there is a panic. Some crisis is happening in the economy, like what we witnessed, the COVID crisis, or there could be financial crisis, or there could be news that the bank is in trouble. Normally that is what happens. And say a lot of depositors suddenly come and then ask for the deposit back. So you don't need all the depositors to come. Only like all you need is a critical number of depositors to come to the bank. Now let's see what will happen if more depositors turn out. Say in my last example, I said 25 depositors came. Let's now assume that instead of 25, 79 depositors turned up and withdrew their money. And bank has given 1 rupee 28 paise each to 79 depositors. Now, what these people go home with their 1 rupee 28 paise. But remember, there are still 21 people waiting for their money back. Now, you can do this calculation later and check. But if bank has paid out 1 rupee 28 paise each to 79 depositors, will the bank has got any money left for the other 21? The answer is 0. So, bank will not have any money for the remaining depositors to pay. So, the remaining depositors will of course be worried. So, once the number of depositors who withdraw the money increases, the remaining one per patient will go panicky. Like, because once the number crosses 79, they know that there won't be any money left with the bank. So, this fear that there will be no money left, if more and more people start withdrawing their money, then by the time I go to the bank, my money will not be there. So this panic makes more and more people to come to the bank and withdraw their money, even if they don't have an emergency. So if that happens, then bank will run out of cash and it will close down. And this is what is called a bank run. Now, this do happen in real life, and it happens more frequently in cooperative sector. You probably might have come across bank runs in cooperative sector in India. So basically, the diamond tubing model shows if enough people take their money out, bank run out of cash and it will fail. So, what are the solutions? Of course, from the very nature of this thing, we can know that one solution could be to not to create that panic among the depositors. So what can be done to not to create that panic? One, of course, is to give a deposit insurance. What's a deposit insurance? Like if you have invested your deposits in a bank, there is a government insurance that at least some minimum amount of your deposit is insured, like irrespective of whether the bank collapses or not. And in India, 5 lakh rupees deposits is insured by Deposit Insurance and Credit Guarantee Corporation. Now, this is one solution, and this is actually an important policy prescription given by Diamond and Tubing in their theoretical model that they actually convince the policymakers that it is important to have deposit insurance so that depositors will not panic and they will not take their money out, and that will prevent bank run or bank collapse, because bank collapse can be a chain reaction. Now, of course, deposit insurance is not the only solution. There could be other solutions like a lender of last resort. What is a lender of last resort? It is like if a commercial bank or any financial institution under the regulation of the central bank, that is Reserve Bank of India in case of India, if it collapses, then before it collapses, it has the provision to take uh, unlimited amount of money from the central bank so that the banks won't run. Now, the third solution is, of course, to stop people from withdrawing the money. Put a cap on how much money people can withdraw. Give depositors their money in small amounts. Now, don't let them to take the entire money in one go. Now, in India, if a bank reaches a threshold level of risk, then automatically it triggers the prompt corrective action framework from RBI. So before the news reaches the depositors that the bank is in trouble, the internal inspection system will report to the bank, to RBI, that this particular bank is running into the risk of a run. So before that, the bank RBI would implement the prompt corrective action. And there could be other solutions like capital regulation, like banks have to follow the RBI instructions on how much it can invest, where each sector, how much bank can have exposure. So these kind of preemptive actions, regulations by the central bank of a country also prevents bank runs. Now, so far I talked about Diamond and Rubik's influential work, which gave this realization that banks are performing an important role in the economy as financial intermediary. But this also generates the risk of bank run, and the risk of bank run can be reduced by providing deposit insurance. Now, let me move on to the contributions of vendor banking. Some of you might have heard about Great Depression. The Great Depression was a long period of 15 years when economies across the world collapsed. The GDP fell, the unemployment was rising. In fact, it was far worse than the COVID crisis that we witnessed now. So traditionally, it was believed that the Great Depression happened because there was a fall in the aggregate demand, which made people not to spend their money. Companies were also not spending money, and that was responsible for the Great Depression. So, it's a traditional view. Indeed, it happened that when stock market collapsed during the Great Depression time, people who invested in stock market, they lost money, so their consumption demand fell, and companies were also not able to raise money from the stock market, so their investment expenditure also fell. So when both consumption expenditure and investment expenditure fell, it led to an overall fall in the aggregate demand, and therefore the GDP fell. So that made the great economist John Keynes to give his famous recommendation that government should spend more money during times of crisis or depression to help the economy grow through Keynesian income multiplier. So government is the only sector which is left which can afford to spend money without thinking about the demand. So higher spending by the government should revive the demand, and it should drive the GDP. So this was a solution given by Keynes, that during times of crisis, increase the government spending. Now, Milton Friedman had a different view on the Great Depression. Now, his view was that problem was that people were withdrawing the deposits from the banks. So banks did not have deposits to give loans. Now, the money multiplier theory in economics says that bank collects deposits, they make loans out of it, and those loans create fresh deposits, and those fresh deposits creates fresh loans, and the cycle goes on. Now, this is how the money supply increases. Now, Friedman and Schwartz, in their 1983 paper, they showed that this was responsible for the Great Depression because people took their money out from the banks. So banks were left with no money to give loans, and therefore the economy collapsed. In fact, they actually blamed US Federal Reserve, that is US Central Bank, that US Federal Reserve should have responded to a crisis by increasing the money supply. so that it would not have prolonged the Great Depression for so long. So this was the explanation for the Great Depression given by Friedman and Scholz. Now, Bernanke broadly agreed with their diagnosis that yes, in fact, Federal Reserve should have increased the money supply during crisis time. So, in fact, actually during in 2008 financial crisis, Bernanke himself was the chairman of Federal Reserve, and he followed the prescription given by Friedman and Scholz, and he actually cut down the interest rates to zero, which is called a zero bound, and he embarked on a quantitative easing and flooded the financial market with money. And that is how many people believe that he saved the US economy from another Great Depression. So far, good. Now, but this is not what for Bernanke got the Nobel Prize. He got the Nobel Prize for his analysis for the Great Depression. He gave a novel explanation why the Great Depression prolonged for so long. Remember, Keynesian diagnosis was that it was a declining aggregate demand that created a Great Depression. And while Friedman and Scholz, it was the declining money supply that created the Great Depression. But Bernanke said no, these are only partially explains the Great Depression. The what actually happened during Great Depression was that banks actually collapsed during a crisis, and with their collapse, the valuable information on creditors were lost. Like banks collect valuable information about the borrowers, your KYC, your credit worthiness, your income, your occupation. Now, when the bank fails, these valuable data about borrowers is lost, and these borrowers find it difficult to access loan from somewhere else. Now, the large firms were not affected because they could raise money from the bond market, from the stock market. But the small borrowers like household enterprises, farmers, they were not able to, their access to credit market was cut off. And because when banks shut down, they got cut off from the loan market, their spending also was stopped. And because during the Great Depression, banks' failure cut off credit access to the small borrowers, they therefore did not have the money to spend, and that caused the Great Depression to prolong. So this was the new finding given by Bernanke. So what was his recommendation then? If Keynes has recommended, okay, increase government spending during financial crisis, if Bernanke has, if Milton Friedman has suggested increase money supply during financial crisis, now Bernanke's recommendation was that banks should be regulated more carefully during crisis time. Don't let banks collapse. It could be because it could then accelerate the crisis into a bigger crisis. So this was a 1983 paper for which he got the Nobel Prize. Now let me take another 10 minutes to talk about some modern developments which is posing some challenge to Diamond Jubilee as well as Friedman's contribution. So some potential challenges to Nobel laureate work, which came first from the Bank of England quarterly bulletin in May 14, where the bulletin article actually challenged our so-called textbook thinking about banking. So textbook thinking comes from Diamond and Dubik and Friedman and people like them who developed these theories over the years. But Bank of England says, sorry, no, this is not how the real world works. They talk about two misconceptions we have about banking. First misconception is that banks are intermediaries collecting deposits and giving out loans. That is what we heard so far. But Bank of England says no, that is wrong. They say that banks actually don't convert deposits into loans. In fact, Bank of England says it's opposite. Deposit don't lead to loans. It's actually the loan that lead to deposit. It's counterintuitive. First, the loan is created, and then that lead to deposit creation. Now, how does this happen? Now, imagine you go to a bank and ask for loan. What do bank do? Bank will credit the loan amount to your account. So, which means that bank has credited a deposit in order to create a loan. Now, so first the loan decision was taken, and then the deposit was created. Now, which means that banks don't convert deposits into loans, but rather banks convert loans into deposits. Now, so this modern view about what banks do actually poses a challenge through diamond and ruby financial intermediation model. Now, the second misconception that the Bank of England challenges was, textbook thinking is that the central banks control what is called the base money or reserve money or what is called the M0. Now, by changing the reserve money through money multiplier, money supply gets affected. Now, this is our macroeconomic theory says. So, but then the modern view is that it is not the central banks. Central banks don't change the reserve money. What central banks change is the policy rate or the interest rate. Like every 2 months, you see here the RBI announcing the monetary policy statement in which RBI changes the interest rates. Now, they decide the interest rate, and central bank does not choose the reserve money. So, how does reserve money get decided? So what the banks do is, first banks decide how much money to lend, and to give this loan, they create deposits. And when they create the deposit, a part of the deposit has to be kept as reserve money with the central bank because of the reserve requirements. Now that changes the reserve money, and so it is the other way around. So it is not the change in reserve money that causes changes in money supply, but it is the lending decision of the bank that changes the reserve money and therefore the money supply. So it is completely opposite of what Bernanke was saying, that when he explained the Great Depression, when he said that it was the failure of the banks that caused small businesses to lose their loans and therefore it prolonged the Great Depression. Now, well, the modern view is that it is not the central banks that is responsible for the money supply. Central banks decide the interest rate, and based on that interest rate, banks will decide how much money they wanted to lend. And this is actually interesting because what I wanted you to notice here is that even the Nobel laureates whose contributions has been recognized also comes under challenge. Now, as the famous economist Keynes once said, when new facts emerged, I changed my mind. So, in that sense, when new thinking comes, old ideas get challenged. But that doesn't mean that we don't celebrate the old ideas. So, the Nobel laureates' ideas is exciting because they were the first one who came with a conceptual, theoretical, and mathematical explanation about how banks work, and so and also in the process how it generates the risk in the system. So we should celebrate their contributions, and but we should also be welcoming of the new ideas and be open to changing our views when new ideas emerge. So I will stop with that. Thank you for your patient listening. And I will take questions if there are any. And put your hands.
Thank you, ma'am, for the talk. Regarding crisis and other problems, another major problem is like big company heads or chairmen taking a lot of amount of loan from reputed banks, from many reputed banks, from a consortium of banks at the same amount of time. They're probably fleeing away. I don't know. So, how do like banks deal with the losses caused due to the same? Like Malia owes 9,000 crore, Nirav Modi may owe Choksi 13,000 crore. So, how do they actually deal with this type of problems?
See, individual frauds like this that won't lead to a systemic crisis. Systemic crisis happens when, as we saw, so when there's a system-wide risk like COVID crisis or a financial crisis, when people as a whole their income falls, or the people who have taken loans from the bank, their businesses collapse. So it's like a systemic risk. When systemic risk happens, then it leads to bank runs because it's like it's a risk which affects across board, across all banks, across all borrowers. But this individual risk that banks face from frauds, that actually has to be dealt at the bank level. So in case of a particular bank, those loans will have to be written off and it has to be recapitalized.
So whoever is the owner of the bank will have to write off those loans as loss and will have to equally capitalize the banks with the new capital.
And ma'am, what are your opinions about the UK financial crisis?
Uh, let's keep the questions within the purview of my talk, but still I would give some general remark on that. The problem with UK's case is that once it left EU, it actually closed UK's doors to international trade because EU had trade agreements with different countries and different blocs. Now, once you quit EU, then you don't have access to those markets, and therefore you will have to individually enter into trade negotiations with countries, and then when you individually negotiate with the countries, you may not get it in the same favorable terms with as you were in a union. So that affects UK's case. Plus the UK economy, the competitiveness affects because in today's global world, when things are competitively produced in China at much cheaper rates, now you have to compete with that kind of level of competitiveness. So that could be another factor that UK is facing.
Thank you, ma'am.
As a follow-up,
Yes.
your first boy's question. Like, let us say, for example, Punjab National
Huh.
Bank, Modi and those things. I think their debt was to the tune of about, several thousands of crores. And you say that particular bank will take a hit. And the bank then will have to sort of write off the loan
Yes.
and reposition itself.
Yes.
Supposing if the magnitude of the scam is so much, how does that bank really survive? Like, for example, 15,000 crores. I don't know the kind of basically the capital with which these banks operate, but isn't it really so much for the bank to survive
No.
such loss?
No, actually, that won't happen because there is sectoral exposure limits for banks. So, a particular out of its total portfolio, a bank cannot give loans or expose its particular portfolio to a particular individual or a particular sector beyond that threshold limit prescribed by RBI.
But how does it make up for the loss? Let's say you write off.
In case of public sector banks, government will capitalize.
So is it the government is doing?
Yes.
Taxpayers.
Thank you, ma'am, for a very insightful talk. I had two questions actually. Firstly, regarding bank centralization. What effect does centralization or decentralization of banks have on the risk of a run?
What do you mean by centralization?
As in, when Indira Gandhi, during her prime ministership, centralized all the banks
Oh, you mean
regulation.
you mean nationalized?
Nationalization.
Okay. So the risk between nationalization and bank run.
Yeah.
Theoretically, it should reduce bank run because when the depositors have the knowledge that bank is owned by the government, then the trust factor increases. After all, banking runs on trust. So once you know that your bank is owned by the government, you have this assurance that it will not run out of cash, that it will not collapse or fail.
But this again depends on how much trust the people have invested in the government in question.
Of course, I mean, if you see, look at the deposit levels in SBI and other private sector banks, you can see why SBI is able to attract all the deposits. It's precisely because people have this assurance that government is backing the bank.
And another question was regarding mergers. During the 2008 housing bubble, we saw that several banks which were failing merged to try and consolidate their assets and recapitalize upon them, which eventually led to a bigger problem when the merged banks itself went into a run. So, how do mergers affect the risk of a run, and should they be avoided, or is more regulation required? What's your take on that?
See, theoretically, bank mergers will increase the profitability of bank, will improve the performance of the banks because then if a bank with a bad balance sheet is merged with a bank with a performing balance sheet, then it actually takes care of the bad performing bank. Of course, that is not a solution for bank runs. The ultimate solution is, of course, better regulation, better supervision of the banks, and that will give an early warning to the regulator that when bank reaches a particular risk threshold, then you know that it's time that you intervene and freeze the further expansion of the bank. So, of course, regulation and supervision cannot be replaced by any other.
Thank you.
Time up? Okay. Thank you for your active participation.
Thank you, Dr. Sebastian, for the informative. Very precious addition to the academic community. Having done his PhD at the National Chemical Laboratory at Pune, he went on to do his postdoctoral fellowship at Ehime University, Japan. His amazing insight into innovations in supramolecule chemistry is inspiring to us. Recently, he was awarded
And bigger molecules getting chopped into smaller molecules is called lysis actually. Protein, for example, when you eat a piece of meat, your enzyme, proteases or peptidases will cleave this protein into several amino acids. We can also do similar reaction, for example, saponification. If you take a triglyceride and put sodium hydroxide, you get soap out of that. But at the same time, you will get some byproduct, which is glycerol. When nature does this reaction, they don't make any material or any waste actually. They are waste free. Even if there is a waste, that will be recycled actually. So it's a zero waste reaction. Natural reactions are zero waste reactions. And I have written few more other reactions, for example, making the protein actually from amino acids by the ribosome. And in that process also there is no effective waste when nature does. We can also do the same peptide synthesis in the lab with a lot of solvents and coupling agents and catalysts, etc. And these are all waste. And finally, you won't get perfect yield actually. You may get 50% or 70%, and remaining there will be unreacted material, sometimes some other byproduct. That means you have to purify that. That involves a lot of other chemicals and media, for example, silicon. So this all leads to waste when the chemists do reactions. I take a simple example here. Starting from phenol, for example, here, phenol to paracetamol, you can do this for reaction and you can get phenol. In every stage, for example, in the first stage itself, you get two products, actually, alternate of phenol and paranate of phenol. You want only the paranate of phenol, you get the separation. Then, of course, the reduction and the process. Every stage you have waste or material which you don't want. And sometimes you require high temperature reagents, catalysts, and other activators for the reaction to happen. Then we do. And as I have mentioned, often will give low yield, some byproducts, and sometimes it's not very selective. And this is an estimated statistics actually. For every drug synthesized, every kilogram of drug synthesized, we generate about 100 kilogram of waste. Even a small synthesis like this. So that is the time, and chemists today chemists have mastered to make very complex molecules. These are some of the molecules which have been synthesized by chemists who got actually very complex molecules which are obtained from marine organisms actually which has been synthesized. This is the broad spectrum anti-cancer compound Taxol which has been synthesized by Casey Nicola in 1994. This is Windblast, and this is another anti-cancer compound. This is Azadirachtin which has been synthesized by Stephen Lane, Cambridge University. In his latest academic paper, he writes, it has taken 22 years, 40 postdocs, and 22 PhD students to make this molecule actually in few milligrams. So, what is the use if you synthesize, if you make synthesis like that? The fundamental objective of any synthesis is to produce some material which is useful. When properties are our goal, such complicated synthesis and such time-taking synthesis to give 1 milligram of products after 22 years is not worthy. The current people, I mean, the community thinks that way. And this is the time when Barry Sharpless, he got the first Nobel Prize in 2001. That is the time he introduced this term click chemistry. There are some reactions which are called click reactions. He just named it click reactions. So how the click works? The reaction should be wide in scope. It should not be restricted to some set of reactions. It should give high yield, and it should give inoffensive byproducts if at all it gives any byproducts. And it should be specific, actually, stereo or regio specific. Process should be very simple condition, and of course it has to work in presence of water or air actually. So you don't need special conditions. Special condition means cost. So these are, and ideally there should not be any purification required. If at all, it should not be chromatographic purification. These are the criteria. And such reactions are usually exothermic reactions, or you can say spring loaded reactions. The A and B are in a higher energy state than the product C. So such reactions are click reactions. This is just like clicking your buckets, I mean, belt buckets actually. Two entities bring together and click, no byproduct. So this is the idea he has proposed. And he has also suggested a few reactions actually. These are the reactions. Click reactions, people often confuse with this particular reaction, azide and alkane giving a trisolate. This is not the click reaction, this is one of the click reactions. So this is one, and the deal salt reaction is one, then oxide ligation is one, and this kind of opening of strained aziridines or epoxide, and also thiolene, and there are other reactions, TCO tetracycline reaction. There are several such reactions. The most famous is this one. So this is the reaction. This is initially it is called Huisger reaction. If you have an azide and alkane, if you heat at very high temperature, about 160 degrees centigrade, it will give two products actually, one for isomer, this R1 and R2, the relative positions, which matters. So this is 1,4 oriented and or decorated, and this is 1,5. You get a mixture actually. This was a useless reaction. It was reported in 1963 because it gives mixture at very high temperature. Most of the solvent cannot withstand 160 degrees centigrade. So this was only in paper actually, and that is the time Meldel, this Morton Meldel, he was doing some peptide synthesis. He was doing some reaction, and I'll go to that slide first. Yes, he was doing this reaction. He wanted to make a wine on here actually. So he wanted to start a terminal acetyl and treat with azyl chloride. This is a known reaction. This is not even copper one. I'm sorry for that. If you have copper, this will make this kind of vinyl. This is already known. So he wanted to make in a peptide. Unfortunately or fortunately, his peptide had another azide molecule somewhere. And what has happened is instead of this reaction, the azide alkane got clicked. So this was just an accident or a serendipitous discovery which Mendel has made by doing this particular reaction. I will go back to the previous slide. And that is the same time. This paper was published in 2002 April actually, and after 2 months, this paper was published by Sharpless. So he has done in water actually. Sharpless has done the same reaction in water using copper catalysis. The beauty is that it reacts at room temperature. You don't get 160 degrees centigrade. It doesn't give two products. It gives only one product, the 1,4-di substituted product. So now this is very, very useful reaction because you can drink anything. Imagine if it's a limit, you can say. So this is a Sharpless paper. Actually, he has showed that all kinds of functional groups. Chemists, we deal with different chemistry and we have different functional groups. And some of them are not complementary actually, because if you do one reaction, some other side gets reacted also. So that is called selectivity actually, or functional group tolerance. And he has shown that all kinds of the common functional groups can be tolerated by this reaction. I mean, it doesn't affect other functional groups. That's very interesting again. Now, that is the same time Carolyn Bertozzi was looking at something in cell actually. She was looking at glycans. This is a very busy slide, I don't read actually. I will tell you one whole story. So she was looking at glycan. Glycan means sugar, the polymer of sugars actually. In our body, in each cell, actually, eukaryotic cell, the outside of the cell is covered with sugars, actually, a chain of sugars. We have 9 different sugars in us, actually, 9 different types of monosaccharides, which can combine in different form and we can have a number of sugar moieties, and which is not studied well because unlike proteins, there is no mechanism by which you can tag this. Protein, of course, you can tag. There is a GFP. If you encode the GFP gene into the protein of interest, you get a GFP and tagged protein, which is colored now, which will become colored. So such tagging is not possible in the case of a sugar polymer. And she was looking for that, and that is the time this chemistry was reported actually, the azide alkane click chemistry. So she thought, yes, this can be used. But the problem is, how do you do click chemistry with copper inside a cell? You cannot introduce copper. Of course, you can introduce, but that will make some problem for this. Copper is not good for the cells. So you can't use copper catalyzed click chemistry inside the cell. You need uncatalyzed cell. I mean, uncatalyzed reaction actually. Because cell is full of chemicals actually, and that can interfere also with your copper. There are billions of chemical reactions happening in the cell, of course, all of you know that. So the question is, why it is interesting is to track a particular molecule actually. If there is something which can tag a particular molecule of interest in a cell, we can study its properties actually. For example, this is the whole cell, each of your protein. If I want to study one particular protein, I want to tag only one of you. I will put a cap which is blowing always, so I can see where this person is always going. So such is the labeling is required in cells to study the function of each proteins. And this chemistry is helpful there also. Than GFP. GFP, the problem is GFP is 238 amino acid. If I want to study a small protein of that size, 200 amino acid, I am tagging another tag which is also really heavy and it cannot function normally actually. So it can be modified, the function can be modified. You want something very, very small. So this chemistry is really good provided you have some mechanism by which you can introduce a tag, a small tag without copper catalysis. That is the idea. So this is, of course, you know, this is an sp hybridized system, which is supposed to be linear. Now this is part of a cycle, cycle-octane. So there is a strain because of that linearity. There is a bend actually here, and this is the strain, about 18 kilocalorie per mole. And if such a strained system needs azide, it immediately clicks. You don't need any catalyst because to release the strain. Because once the reaction happens in the SP becomes SP2 actually. So that has a 120 degrees the angle, right? Now this is 180. So there is a relaxation. So to relax that, it immediately reacts. So now what she has used is that. So she has made a probe. You can connect any probe of your interest. It is a fluorescent material or a drug or anything, and you can introduce. This is like this, really a strained spring actually. So it reacts. This kind of octane. These are different variants to change the reactivity. When you introduce electron withdrawing fluorine, and it increases the reactivity and it reacts really faster. So this is what her idea is, to introduce azide to the cell, and of course she was interested in the sugar part of it, and introduce her probe through this chemistry. So how does she do? Let us see. So this is again, she has gone to the biology and how this particular sialic acid. Sialic acid is at the periphery. In all the sugar forms in eukaryotic cell, the last sugar or the peripheral sugar is sialic acid. And its sialic acid is always outside. It cannot be inside actually. So how sialic acid is produced is like this. So it's an aldol reaction. Most of the reaction which we do in our lab, that is being done in our system also. There is aldol reaction happening in our system. So this is from mannose N-acetyl mannosemic. This is a sugar which we have. And this is of course pyruvic acid, a keto acid. And they undergo aldol reaction, and that's why that's how we get sialic acid. That's how biosynthesized in our body. So what she has introduced is this one now. And that once the sialic acid is generated, that gets incorporated to other proteins, glycoproteins, or other sugar part at the periphery. You have sialic acid. So what she has introduced, instead of taking mannose, she has taken azidomannose. One hydrogen was replaced by azide. So it behaves very similar to this mannose and acetyl mannose. You have only differences. One H is replaced by an azide. Now the cell was fed with this acetyl mannose, and that gets converted to the sialic acid with azide inside the system using the synthetic machinery, biosynthetic machinery actually. That gets converted to sialic acid and then finally get incorporated into the protein or glycoprotein. Now she introduces this kind of tag. This is the tag which reacts. Of course, this is the biotic tag. Now, of course, there is some protein called streptavidin, which will nicely bind with the biotic. So that streptavidin, of course, you can make colored. You can have FITC tag connected. FITC means fluorescent isothiocyanate, which is connected to streptavidin. That means it will be colored streptavidin. So that's how she initially studied this. So FITC streptavidin or streptavidin, both are similar, and that binding is really strong. This amidin biotin binding is really strong. That's what she has used, and this was a paper in JACS years ago. And this is the real picture, her cell picture. You can see the cell membrane is decorated with all this sialic acid, and later she has improved on this one. Instead of using this streptavidin-amidin system, she has directly attached a fluorescent tag, directly a chemical fluorescent, like fluorescein. That is also possible. And of course, people have worked on that. Instead of introducing the alkane first, you can have this kind of ketone, which is also three-membered. Here you have a spatio-temporal control, or temporal control, you can say. If you can feed this with, the cell can be given this one at the time you want, you can shine light, then this will get released to alkane. So So this additional control which chemists use when you want to release the alkane, when you want the chemistry to happen. That is also possible. This is by Geethia and Boots. Again, same chemistry he has developed based on Bertozzi's work. And this is again the cell image. Actually, this is great because the slide is not clearly visible. Now she has taken only, until now she has taken only a cell actually, Jurkat cell actually, a cell line. Now what about in an organism, in a living organism? Can we do this reaction in a living organism? In this case, she has taken an embryo of zebra cell, zebra fish. So that is very transparent. Of course, the biologists know it's a very nice model organism. You can see that without any invasive technique. Actually, you can see what the result fluorescent. So she has fed this material. This is a galactose derivative. Actually, whatever you say. See here, this galactose derivative was fed to that. This is microinjector. Actually, in this case, microinjected to the cell, and again the same mechanism by which it will finally convert to. So this will not convert to anything else. This will directly attach. Galac will be finally attached to one of the glucose or sugar oligomers, and that was also studied at different stages. In this paper, she has shown at different developmental stages, from embryo to a fish. At what stage, what kind of sugar is getting localized, where and what. So such a nice study this science paper was. So this is the chemistry here. So you microinject this one, and that will get deacetylated by there are esterases in the system that will remove all the acetate, and there are of course one kinase is required to make a phosphate here, and then and pyrophosphorylase to make the UDP sugar, and that will get incorporated into the growing chain. Actually, this happens in the Golgi apparatus and endoplasmic reticulum, then finally it exposed to the outside of the cell. So that's what it happens. And when finally it does that, so she introduces the diphos. This is the octane with the tag, fluorescent tag. I don't want to show you what tag. What tag can be anything, but whichever color you want, whichever function you want. This is another chemistry again, which you can do in the cell. This is a tetraene actually. This is tetraene. This can react with this is cyclooctene. Until now, we have talked about octine. This is also strange because this is trans. Because trans, you know, these bonds are opposite, right? This bond is with respect to the double bond. Now you have only 4 more atoms to connect these two ends together, and that is really strange. So the moment you have something like this, it will undergo Diels-Alder reaction. This is the Diels-Alder reaction. This is the Diels-Alder partner, and this will undergo Diels-Alder reaction, and again retro-Diels-Alder reaction, eliminate a molecule of nitrogen, and finally you get this kind of linkage. These two get linked. So now whatever you have R1, R2, of course, this kind of molecules can be easily made. Now, if it is a tag, of course, your molecule of interest is tag. So that's all. This linkage is very simple. Again, this can be done in the cell actually. So let us see application in medicine. We have time actually. So in a drug development process, what happens is you start with millions of molecules. Once you identify a drug target, actually, once you identify a disease, you find some target. Of course, that is a biology part. Then developers say, of course, you need a lot of molecules. You need, this is not a molecule, not 10,000. You need actually millions of molecules to start with for the initial screening. Then lead optimization, lead identification, then clinical trials. It's a brief actually. Each stage is divided into further steps actually. So our limiting factor is this: you have to start with millions of compounds for the initial screening. Now, how do we get? Olden days we used to get from all sources of nature actually. So these are our sources. Extract from the natural sources. Different these are our drugs actually extracted from different sources, plant sources and also animal sources. Now, the modern day drug discovery doesn't do like this. We don't do like this anymore because this is very tedious and the success rate is very less actually. So what we do currently is make a library of compounds chemically, and make we can make 10,000s of compounds in a day using a combinatorial library. For example, click can be used. For example, if you have 5 alkane and 5 acid, if you can mix all them together, you will have 25 molecules in your in the flask. You can do individually also in a well plate, the 96 well plate or 386 well plate, you can have individual compounds. And in one reaction, you have so many compounds, 386 compounds. And you can, so this kind of reaction is very facile. And this click chemistry has been used to make a library of compounds for drug discovery. As I will show you a few examples here. So this is an example. This is an HIV protease inhibitor, which is used for therapy currently. Now people wanted to make an analog of this one, this amprenavir. So what the retrosynthetic pathway is here actually. So they wanted to make something like this. So mimicking that, this is the part mimicking this, and this is the acyl part. So they want to start from something like this and connect this through an acyl alkane, this triazole. So that mimics like the sulfonamide. So that is the, you don't see real mimicking, but the overall, yes, there is a mimic. You are talking about after docking, right? So you take the protein of interest where it binds and do docking and you see similar structure. Now you can make a library of molecules. Here they made less than 100 molecules actually using this chemistry actually. And they found that yes, these two molecules are almost, this is as good as this and this is much better than that. So this is under clinical trial. Very simple chemistry from knowing one drug to another, I mean, developing one drug to another one actually. So this is very different chemically. It's another company actually. This is under clinical trial. And this is Chagas disease. Chagas disease is caused by a protozoa called Trypanosoma cruzi. So it's like our malarial parasite. So that organism has half the life cycle in our body and half the cycle in the fly. Very similar to this one. So same protozoa. So what it does is how it evades our immune system is it steals. We only have the sialic acid. I told you the sialic acid, the sugar. So we only have that. The parasite doesn't have that. So that means once the parasite is inside the cell, our immune system will immediately act and kill that, right? So it doesn't happen because this parasite is so clever. It steals our sialic acid from our body and put it across that actually. The parasite will become covered with sialic acid. So there is an enzyme in that organism called trans-sialyl transferase. The enzyme which steal our sialic acid and put it on that. So that is an enzyme which is helping to evade our immune system. So now people have made a library of molecules. Actually, this is Robert Field from the East Anglia, England. Actually, he made a click library of this. This was clicked with several other alkanes and found that this is the process of that stealing process. This blue one is the that enzyme which steals. So this is the bacterial, the protozoal. The sugar actually, protozoal cell and the sugar, and this is from the human. So this is how the transition state is. That the sialyl group will transfer from this to that. This is just a schematic. This is not actually the real picture. So this process has to be blocked. Then you have a drug for that particular disease, or Chagas disease. So to mimic that, you need a galactose derivative which has a span to this side also. So that's what he has made, a galactose with this kind of this amine or this aniline connected through triazole, which gets stuck here actually, so that your substrate cannot occupy that. It's a competitive inhibitor, which is again under clinical trial for Chagas disease. So these are approved drugs actually using the click chemistry. This is Tisagrelor, or this is a blood thinner, and this is an antibiotic. This is antibiotic is being used, and this is anti-cardiac treatment for epilepsy. Actually, this particular called rufinamide. This is using the same chemistry, and the other one is erythromycin is again an antibiotic for pneumonia, bacterial pneumonia. Then the other one is a galactin inhibitor, having this sugar analog. That is for pulmonary fibrosis actually. And these are some of the drugs under late stage of clinical trial 2 and 3 actually. This is voltinib. The first one is for lung cancer, renal carcinoma, renal cell carcinoma in phase 2 clinical trial. The other one is also for prostate cancer. Actually, this is an inhibitor of that particular an inhibitor of an enzyme which produces androgens and estrogens actually. So that means for breast cancer and prostate cancer. This is again in the phase 2 clinical trial. The other one is again
For anemia, this is for anemia treatment, this particular molecule. This is a prolyl hydroxylase inhibitor. Again, through library it came through. Then this one is an antibiotic for skin infections. And the other one is for again for anemia. This is erythropoietin, I think erythropoietin activator. So this is again for anemia. Then the other one is for pain. These are the molecules in the late stages of clinical trials using the same chemistry. Very quick actually. So in 2002 this has happened and molecules are in the market and also in several clinical trials. Really quick. This is another one for this is for HIV actually. This is a HIV-1 viral factor antagonist actually. This is a non-molecule and they have made a library similar to that, and this is much better than this. This is again under clinical trial for HIV treatment, anti-HIV treatment. Vancomycin is a very wonderful antibiotic actually. The problem though is the bacteria get very easy resistance against them. Bacterial resistance is very severe, especially for vancomycin. Vancomycin resistant bacteria are so many. So now, how do we make vancomycin? Is a very complex molecule. This has been synthesized by Nikolov. Nikolov has synthesized it, but it's a very complex synthesis. You can't use that for a medicinal purpose. So what they have used, they have isolated this. Vancomycin is isolated from the natural source, and there is of course a disaccharide unit here, two sugar units are there. So now they have introduced this azide through using a glycosyl transferase, using this glycosyl donor, having this azide. Now you have a monosugarated or a glycosylated ablygon. This is the ablygon part. Now you can do click chemistry with different sugars. Each time bacteria develop a new, resistant, you develop a new drug actually. You click with another one and you have another one. So randomization, you can randomize the glyco part actually, the disaccharide part. So that is being used actually. So another so cancer vaccine, people are talking about cancer vaccine. In most of the cancer, this GalNAc, galactosamine, is overexpressed, not you can say overexpressed actually. Most of the protein in the cancer cell has this GalNAc, too much of GalNAc. So GalNAc can be a target for generating anti-cancer vaccine actually. So people are, for example, Samuel Danishevsky is working for last several years for making this kind of GalNAc derived peptides actually. You need several of them to make an immunogenicity actually. If you want to use it as an antigen for to inject into the system, you need something which is not harmful for your system. So you need a peptide which is not harmful and on which you want to develop this kind of arrays of sugars, which is you can say a cancer sugar actually. So that is being done. I think this is also in clinical trials. Late stage, I think. This is again HIV vaccine, similar. This is HIV has a protein called glycoprotein 120, which has mannose. This kind of mannose actually on one of this protein actually GP 120, and that people want to make as a possible antigen. So again, people have made this kind of cyclic peptide, thymine, lysine, glycine, proline, all those things. So we can make a cyclic peptide synthetically and attach this kind of alkane and introduce this kind of oligomannose. Here they have only used tetramannose. They have tried all mannose. 9 mannose is not required actually for immunogenicity. You need only 4 mannose, and that is also under clinical trials for HIV infection. So this is, I think, one more, and I will stop. So this is again another click which I have mentioned. This is doxorubicin, which is an anti-cancer compound. You have seen people under treatment for cancer, they get really weak. They lose their hair and they become really weak. Why? Because there is no selectivity for this particular drug. It can kill the normal cells. That's why they have become weak. So how do we give this particular compound to only to the cancer cells? So this is what addressed in some of these papers. This is one of the such papers. So here doxorubicin, the blue part is only doxorubicin, which is the cancer drug. The other one is a derivative, which is not a drug, actually it doesn't kill anything. So you can introduce this to the system by IV or by, I think this is IV only and not oral. So IV, through IV you can introduce this one. Then this is a polymer, biopolymer actually, which is uh, a sugar-based polymer, biopolymer, hyaluronic actually, and wherein you can have this tetrasid. Tetrasid chemistry I have mentioned you already. So the moment it sees this cyclooctene, transoctene, it will react. And once it reacts, it releases this particular drug actually. I have shown the mechanism here. So once it reacts, this kind of thing, it will kick the drug out actually. So the NH, the lone pair from here will go there and the double bond go there. This bond will go to there and it will cleave the carbon dioxide and drug will be released. Once click is there, it will release actually. So now this is a polymer you can inject to the tissue where the cancer is, if you know the cancer tissue. So it will selectively kill those cells. So this is again in clinical trials, phase 2 clinical trials. This is another one. This is similar mechanism where they are using. Again, cancer has some overexpression of some of the enzymes. For example, topoisomerase is overexpressed in all types of cancers. So you can have an antibody to the topoisomerase. I'm just giving an example, wherein you can attach this kind of transoctene which is connected to the drug. Now this is not active. The drug is connected. This is not a drug anymore. This is a pro-drug. The moment then you introduce the whole thing to your system, it will selectively go to the cancer cell because you have an antibody connected to antibody specific to that cancer protein actually, right? Topoisomerase, for example. After some time, you introduce the other one, tetrasid, in some form. Then it will release this particular drug only at the cancer cells. It will release only at the cancer cell and selectively you can release. Not only that, you can, if you want to take a biologist, for example, if they want to take some of the load to selectively to an organelle, for example, endoplasmic reticulum or lysosome or Golgi apparatus, there are small molecules like peptides which can selectively go to that particular compartment in the cell. And if you want to take a load to that cell, just attach using quick chemistry and you can take that load. So that is the beauty of this chemistry. Biology has been, really, made use of this chemistry a lot actually, biology and medicine. Not only that, polymers also, you can have different kinds of polymers, right? You have A polymer, B polymer, you can link together and have advanced properties. You have a polyethylene glycol which is hydrophilic, and you can have polystyrene which is hydrophobic, and you can click together and you can make a single molecule and you have better properties. All kinds of this, all some of those things I have just copied, and you can see all kinds of star polymer. And this is, for example, this is having a OH actually. This is hydrophilic side and hydrophobic side. You have an amine here under acidic condition. This will become water soluble fraction. Water soluble mode. Half is become half water soluble, half become water insoluble. So we'll have a core shell. This will be exposed outside. If you reduce the pH to alkaline pH, it will go to the other side actually. Alkaline pH, this will become N plus 2N. Then it will go to the inner side, and this will become minus, and it will go to outside. So you have switching of material, and basically that is property. That's what everybody wants actually. We have some control using light or pH or any other stimulus. Yeah, all kinds of physicists of you know all this material. This is fullerene, then buckyballs. You can attach anything to that to get more and more property. This is again graphene. You can attach anything, whichever you want. So imagination is your limit. That's what I want to tell you here. This you don't need to read. Just imagination is the limit. Anything can be coupled together. As long as you have, you can make an azide and alkane. So that is the limit of this chemistry. Application in biology, and all I have already mentioned. Some of them you can track anything. You can target anything to a particular organelle of a cell. Actually, that is the precision you have with this chemistry. And I think chemistry is unarguably simple but very powerful too. I think you will agree with me that this is worth of a Nobel Prize. Thank you very much.
Thank you, sir, for I had a couple of questions. In the examples we have seen for click chemistry, mostly addition reactions have been seen, like dipolar cycloadditions are such, or maybe starting a ligation is again an addition reaction at heart. So can this principle be extended to substitution reactions per se, or is it limited to addition reactions?
Yeah, the problem with substitution reaction, you are talking about waste, right? One of the criteria is it should not generate any waste. In substitution reaction, you are kicking out your reacts with the Y, right? Your nucleophile is kicking out your leaving group actually. So that's bad in terms of atom economy. You are talking about atom economy here. Here you take A and B, you get 100% of the product. All the atoms are in the product actually. So people usually look for cycloaddition chemistry or addition chemistry.
And we have seen, we essentially are adding newer groups in biothermal chemistry. We add transcyclooctane or cyclooctane to the cellular environment. Wouldn't that perhaps cause perturbation to the cytoplasm, given that it is already a very crowded space? How do you control perturbation?
It is much better than the perturbation introduced by tagging a GFP or any other system, which is 238 amino acid, which is quite heavy. Of course, it may be there, but there should be control, of course.
And in all the pharmaceutical applications we have seen, the azide group has been with the dipolar addition using the azide has been applied in all these instances that we saw here, most of them anyway. So what about the azide makes it such an excellent functional group for this purpose?
Because that's very inert, because it doesn't react with anything in the cell actually.
And thank you, sir. Final question. Since we have seen that it doesn't react with anything else, the high selectivity of these reactions, does that mean we can eventually render protecting groups unnecessary? So for conventional synthesis, we often have to protect some other group using, say, POC or something else, and then carry on the reaction and then deprotect it so that we can move on. So using click chemistry, would it perhaps render the POC and other such protecting groups unnecessary eventually?
Actually, the azides are used as an intermediate to expose amine at the later stage by reduction. So that is, you can't say as a really protecting groups. You can convert azide to amine actually. So you can avoid protecting groups. You don't need to make an NH-BOG, for example. You don't need to start with an NH2. You can start with an azide or halide, connect nucleophilic substitution, make an azide. That you can expose amine at a very later stage because azide usually doesn't react with anything unless you have these two copper and this one. So that's it. In effect, it's a protecting group kind of thing.
Thank you. Sir, about the cancer vaccine you mentioned.
Where is the person? Where is the
cancer vaccine you mentioned? Like you have a peptide sequence of certain kind, and you have many N-acetyl galactosamine on it. So N-acetyl galactosamine is also available on the cell surfaces, normal cell surfaces.
Yes.
Other than cancer cell, on cancer cells, it might be overexpressed.
Yes.
So how do we, after introducing a molecule, if we as an antigen, how do we like render protective, how do we protect the normal cells and how do we target our body to develop an immune response to cancer cells only?
I think it's only statistics because cancer cell has more of this one, so it selectively goes. That is what I would expect actually. So it's only the relative number, which is normal case GalNAc is very less. Of course, GalNAc is a transient term most of the time. It's a post-translational modification between like phosphorylation. Wherever phosphorylation there is GalNAc is also possible at some other time. So it's more like a transient thing actually. But this, in the case of cancer, this is all the serine, threonine, and the tyrosines are GalNAc related. I think it's a mere number.
Thank you, sir.
Take one last question. Very good afternoon, sir. So I do have a small question. You told that cycloalkyne and azide, we can take any derivative or we can couple them. Then is it possible to implement this to make cross-linking between any polymers, suppose organic polymers like polybenzimidazole or like
That's what I have shown last video. I have just run through anything.
so
Imagination is your limit as long as you can put these two. So that is the final statement.
because it has good implementation for perforation and FO and RO.
What is that for?
Forward osmosis, reverse osmosis,
Okay.
perforation.
Right. Anything is possible. I don't know much about reverse osmosis and forward osmosis, but anything is possible to connect as long as you have azide and alkyne. Thank you.
On behalf of the ANVESHA team, I would like to thank all the speakers for their expert insight on this year's Nobel Prize. I would also like to thank the Honorable Director, faculty members, and the student committee for attending the Nobel for attending the Nobel Exposition series. Team ANVESHA hopes we all have learned something new today and fueled our enthusiasm for science. We will now break for lunch and regroup at 3 p.m. for the workshop on simulations at TSB Seminar Hall. Thank you, everyone.